The evidence came gradually, piece by piece, over decades of planetary exploration. In 1971, NASA's Mariner 9 spacecraft became the first to orbit another planet. When the global dust storm that initially obscured the surface finally cleared, the orbiter's cameras revealed something unexpected carved into the Martian highlands. Valley networks. Thousands of them. Branching tributaries that looked remarkably similar to river systems on Earth, etched into terrain dating back 4 billion years, to a period geologists now call the Noachian epoch. These were not the channels carved by catastrophic floods that scientists had already identified elsewhere on Mars. These valleys showed the unmistakable signature of persistent, steady flow over long periods. Rain-fed rivers, which meant atmosphere thick enough to support a water cycle, which meant an ocean to evaporate from. But here is where the story gets uncomfortable. Mars should never have been warm enough for liquid water. The young sun 4 billion years ago was about 25 to 30% dimmer than it shines today. This is the faint young sun paradox, and it affects our understanding of early Earth as well. On Mars, located 50% farther from the sun than Earth, the surface temperature should have been well below the freezing point of water, even with a thick carbon dioxide atmosphere providing greenhouse warming. The calculations were clear. Mars should have been frozen solid. Yet the valley networks exist. The proposed shorelines exist. The clay minerals that only form in the presence of liquid water exist, concentrated in the oldest rocks. Scientists named this warm, wet period after Noah because of the water. The Noachian period stretched from about 4.1 billion years ago to about 3.7 billion years ago. During this window, something kept Mars warm. Volcanic outgassing might have pumped enough greenhouse gases into the atmosphere to overcome the faint sun. Massive asteroid impacts during the late heavy bombardment could have injected heat and water vapor into the atmosphere repeatedly. The planet might have experienced episodic warming periods between longer frozen intervals. We are still working out the exact mechanism. But the evidence for abundant surface water during this time is overwhelming. The ocean itself left multiple signatures. Orbital imaging by Mars Global Surveyor and later missions mapped 2 distinct elevation boundaries in the northern lowlands that closely match the elevation profiles you would expect from ancient shorelines. The lower boundary, called the Arabia shoreline, sits at roughly minus 3.8 kilometers relative to Mars' mean elevation. The higher boundary, the Deuteronilus shoreline, lies about 1 kilometer higher. If these are genuine shorelines, they suggest the ocean's depth varied over time, possibly due to climate fluctuations or gradual loss of water to space and underground ice. The northern plains show other features consistent with an ancient ocean floor: smooth, flat terrain with very few impact craters, suggesting the surface was once covered by water or sediment. Polygonal patterns in the ground that resemble features formed by water-soaked sediments. Deposits of minerals that typically form in water. Here is the problem. Mars lost its ocean because it lost its magnetic field. And it lost its magnetic field because the planet is small. Mars has only about 11% of Earth's mass. Its iron core is smaller, contains less heat, and cooled faster. Around 4.2 billion years ago, give or take a few 100 million years, Mars' liquid outer core solidified enough that it stopped generating a global magnetic field through the dynamo process that still protects Earth. NASA's MAVEN mission, which has been orbiting Mars since 2014, directly measured what happens to a planet without magnetic protection. The solar wind strips away the atmosphere. MAVEN's instruments detected atmospheric ions being accelerated to escape velocity and carried off into space by the sun's charged particles. The spacecraft measured escape rates of about 100 grams per second of atmosphere lost to space today. That might not sound like much, but multiply it by billions of years, and you lose an ocean's worth of water. The process works like this. Without a magnetic field to deflect the solar wind, charged particles from the sun slam directly into the upper atmosphere. These collisions transfer energy to atmospheric atoms and molecules, knocking some of them to velocities high enough to escape Mars' relatively weak gravity. Mars's surface gravity is only 38% of Earth's, making escape easier. Lighter elements like hydrogen are lost most readily, but over geological time, even heavier atoms like oxygen get stripped away. Water molecules in the upper atmosphere get broken apart by ultraviolet light into hydrogen and oxygen. The hydrogen escapes almost immediately. Much of the oxygen escapes too, though some reacts with surface rocks to create the iron oxide that gives Mars its red color. This is oxidation on a planetary scale. The planet is literally rusting as it loses its water. Maven measured how this process varies with solar activity. During solar storms, when the solar wind intensifies, atmospheric loss rates increase by a factor of 10 to 20. The young sun 4 billion years ago was far more active than today, with more frequent and powerful eruptions. This means atmospheric stripping rates in Mars' youth were likely hundreds of times higher than current measurements. Computer models that account for the young sun's behavior suggest Mars could have lost an atmosphere as thick as Earth's current atmosphere over the course of several 100 million years. The ocean evaporated gradually as the atmosphere thinned and surface pressure dropped. Some water froze into polar ice caps and underground deposits. Some was lost to space. Some remains locked in minerals and hydrated salts. But the ocean itself disappeared. Think about that for a moment. A world that once had waves and tides and river deltas became a frozen desert because its core went cold. The destruction was not sudden or catastrophic. It was gradual, inevitable, determined by the planet's size. Mars was born too small to hold its water. The evidence is not perfect, and this makes the story even more interesting. Some scientists argue the features identified as shorelines could be formed by other processes. The boundaries are not perfectly horizontal, as you would expect from water that settles to a level surface. Mars's rotation axis has shifted over billions of years due to the redistribution of mass from volcanic activity and ice cap changes. This polar wander could have tilted ancient shorelines, or the boundaries might mark the edges of glacial deposits rather than liquid water oceans. The debate continues. But the valley networks remain. The clay minerals remain. The deuterium to hydrogen ratio in Mars' current atmosphere is 5 times higher than Earth's ratio, exactly what you would expect if Mars preferentially lost lighter hydrogen atoms to space over billions of years, enriching the remaining atmosphere in heavier deuterium. NASA's Curiosity rover, which has been exploring Gale Crater since 2012, drilled into rocks at the base of Mount Sharp and found abundant evidence for ancient lake environments. The rover detected mudstones with chemical compositions indicating they formed in neutral pH water with low salinity, conditions similar to lakes on Earth. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur were all present in forms usable by life. The rocks date to about 3.5 billion years ago, near the end of the Noachian period when the ocean would have been disappearing. Some regions of Mars clearly remained wet, even as the planet dried overall. These isolated lakes might have persisted for millions of years after the ocean was gone, fed by groundwater or seasonal melting. Before you drift off tonight, leave a comment. What time is it, where you are right now, and where in the world are you watching from? The implications of Mars' lost ocean extend far beyond one planet. If Mars was once warm and wet with conditions suitable for life, then life might have emerged there independently during the Noachian period. We have not yet found evidence for Martian life, but we have only examined a tiny fraction of the planet's surface, and we have not yet looked in the most promising locations. Ancient lake beds, hydrothermal systems, deep underground where liquid water might still exist. Future missions plan to collect samples from these environments and return them to Earth for detailed analysis. The European Space Agency's ExoMars rover, delayed but still planned for launch, will drill up to 2 meters below the surface where organic molecules might be preserved from radiation damage. NASA's Perseverance rover is currently collecting samples in Jezero Crater, an ancient river delta, for eventual return to Earth. But here is the deeper question. If life did emerge on Mars 4 billion years ago when the planet had oceans and a thick atmosphere, what happened to that life when the oceans disappeared? Some organisms might have adapted to increasingly harsh conditions, retreating underground as the surface froze. Microbial life on Earth survives in extreme environments including Antarctic ice, deep mines, and hydrothermal vents. Martian life, if it existed, might have done the same. Or it might have gone extinct completely when liquid water vanished from the surface. Or Mars might have never developed life at all, despite having favorable conditions for hundreds of millions of years. The emergence of life might require not just liquid water and organic chemistry, but also time scales or specific circumstances we do not yet understand. The story of Mars' ocean reveals something important about planetary habitability. Having the right ingredients for life is not enough if the planet cannot hold onto them. Earth maintains its ocean and atmosphere because our magnetic field deflects the solar wind. And our magnetic field exists because we have a large, partially molten iron core that sustains a dynamo. We have that core because Earth formed with enough mass to retain heat over billions of years. Mars formed smaller and cooled faster. This is thermodynamics. Larger objects retain heat longer because volume increases faster than surface area as size scales up. Earth's volume is about 6 times larger than Mars' volume, but its surface area is only about 4 times larger. Earth loses heat through its surface, so the volume-to-surface ratio determines how long the interior stays molten. Mars never had a chance. Its fate was determined at formation. This connects to the search for habitable worlds beyond our solar system. We have discovered thousands of exoplanets orbiting other stars. Many orbit in the habitable zone where temperatures allow liquid water. But the habitable zone concept only considers distance from the star. It does not account for planetary mass, magnetic fields, atmospheric retention, or the countless other factors that determine whether a planet stays habitable. Mars was in the Sun's habitable zone 4 billion years ago. It had water. It likely had all the chemistry needed for life. But it lost its habitability because of its size. How many exoplanets that appear habitable from a distance have already suffered Mars' fate? How many started wet and warm but lost their atmospheres because they formed too small or orbited stars too active? The question is not just whether we find water on other worlds. The question is whether those worlds can hold onto their water long enough for life to emerge and persist. The measurements that reveal Mars' wet past continue to accumulate. In 2018, the European Space Agency's Mars Express orbiter used ground-penetrating radar to detect a 20-kilometer-wide lake of liquid water buried beneath 1.5 kilometers of ice at Mars's south pole. The water remains liquid despite freezing temperatures because it contains dissolved salts that lower its freezing point, similar to how salt keeps Earth's oceans from freezing solid. This discovery confirmed that liquid water still exists on Mars, just hidden underground. More recent radar surveys have identified additional pockets of potential liquid water beneath the southern ice cap. Whether these buried lakes could harbor life remains an open question. What happened to Mars is not unique in our solar system. Venus might have had oceans too, early in its history when the sun was cooler, and Venus received less radiation. But Venus experienced runaway greenhouse warming as the brightening sun vaporized any oceans, and the water vapor trapped heat, which vaporized more water until the surface reached temperatures hot enough to melt lead. Venus lost its water not through atmospheric stripping, but through a thermal disaster. The water vapor was broken apart by ultraviolet light. The hydrogen escaped to space, and Venus became the hell world we see today. 2 planets in our solar system's habitable zone. Both likely had surface water early in their histories. Both lost it through different mechanisms. Only Earth retained its ocean, sheltered by its magnetic field and positioned at just the right distance from the Sun. The valley networks on Mars tell us that 4 billion years ago, water flowed across the surface for long enough to carve river systems hundreds of kilometers long. This requires precipitation, rivers, and an ocean to complete the water cycle. The ocean was real. The question now is not whether Mars had water, but what that water means for life, for planetary evolution, for our understanding of how common habitable environments are in the universe. And the story continues, written in layers of rock, still waiting to be read. The physics of atmospheric loss operates through SEV loss, operates through several distinct mechanisms, each stripping away Mars' protective blanket through different pathways. The primary culprit is a process called sputtering. Solar wind particles, mostly protons and electrons traveling at 300 to 800 kilometers per second, slam into atoms and molecules in Mars' upper atmosphere. These collisions transfer momentum. When a heavy ion from the solar wind strikes a lighter atmospheric particle with enough energy, it can knock that particle upward at velocities exceeding Mars' escape velocity of 5 kilometers per second. The atmospheric particle flies off into space. One collision at a time, the solar wind sandblasts away the atmosphere. But sputtering is only part of the destruction. A second mechanism called ion pickup occurs when ultraviolet radiation from the sun ionizes atmospheric particles, stripping away electrons and leaving the atoms electrically charged. These newly created ions respond to electromagnetic fields in the solar wind. The moving solar wind carries its own magnetic field, and as this field sweeps past Mars, it catches the ionized atmospheric particles and drags them along like leaves in a stream. The ions get accelerated to the solar wind's velocity and carried away from the planet. MAVEN's instruments measured this process directly, tracking the curved paths of oxygen ions as they spiral away from Mars along magnetic field lines. The spacecraft detected ion escape rates of about 1 kilogram per second during quiet solar conditions, rising dramatically during solar storms. A third pathway involves photochemical escape. Ultraviolet light breaks apart molecules like water vapor and carbon dioxide in the upper atmosphere. Water molecules split into hydrogen and oxygen. Carbon dioxide breaks into carbon monoxide and oxygen. The light hydrogen atoms, being so light, reach escape velocity easily from thermal motion alone at the temperatures found in Mars' upper atmosphere. They simply evaporate into space. Some of the oxygen escapes too through the other mechanisms. Some falls back and oxidizes surface rocks. Over 4 billion years, this process has oxidized the top several meters of Martian soil, locking oxygen into iron oxide minerals. The planet's surface is a giant rust stain, evidence of water destroyed. Here is why conventional planetary science failed to predict the severity of atmospheric loss. Early models of Mars evolution assumed the solar wind's impact would be minor because the solar wind's density is so low. In the space between Mars and the Sun, the solar wind contains only about 5 protons per cubic centimeter. That is a better vacuum than we can create in most laboratory chambers on Earth. How could such a tenuous flow strip away an entire atmosphere? The answer lies in the timescale and the lack of protection. Even a thin stream becomes devastating when it flows continuously for billions of years. And without a magnetic field, there is no barrier. The solar wind reaches all the way down to where Mars's atmosphere becomes dense enough to resist it, currently about 200 kilometers above the surface. On Earth, the magnetosphere keeps the solar wind at bay 60,000 kilometers out. The difference is everything. Think of Mars' atmosphere as a sandcastle at the edge of an incoming tide. Each wave, each splash of water removes only a few grains of sand. But the tide does not stop. It keeps coming, wave after wave, day after day. Eventually, the sandcastle dissolves completely. The solar wind is the tide. Mars had no seawall. The rate of atmospheric loss depends on several factors that vary over time. Solar activity follows an 11-year cycle on average, with periods of high activity producing more frequent solar storms and stronger solar wind. But the cycle was more intense when the Sun was younger. 4 billion years ago, the young Sun rotated faster and had stronger magnetic fields, producing solar storms far more powerful than anything we see today. Measurements of other Sun-like stars at different ages show that young stars produce superflares hundreds of times more energetic than the largest solar flares recorded in modern times. These superflares would have blasted Mars' atmosphere with intense bursts of radiation and high-velocity particles. MAVEN data shows that current solar storms increase atmospheric escape rates by a factor of 10 to 20. If young Sun superflares were 100 times more intense, they could have stripped atmosphere at rates thousands of times higher than today's baseline. The early assault was devastating. Mars's declining magnetic field made things worse over time in a feedback loop. As the magnetic field weakened, the solar wind penetrated deeper into the atmosphere, accelerating loss. As atmosphere was lost, surface pressure dropped. As pressure dropped, liquid water became unstable and evaporated or froze. As water vapor entered the atmosphere, it was broken apart by ultraviolet light, and the hydrogen escaped. As more hydrogen escaped, the remaining atmosphere became enriched in heavier isotopes, because light isotopes escape preferentially. This isotopic fractionation provides one of our clearest measurements of how much atmosphere Mars has lost. The deuterium to hydrogen ratio tells the story quantitatively. Deuterium is heavy hydrogen, with 1 proton and 1 neutron in its nucleus, instead of just 1 proton. Regular hydrogen escapes to space more easily because it is lighter. Over billions of years of preferential light hydrogen escape, the ratio of deuterium to regular hydrogen in Mars' remaining atmosphere has increased. We can measure this ratio by analyzing light absorbed by atmospheric water vapor. Mars's current deuterium to hydrogen ratio is about 5 to 8 times higher than the ratio found in Earth's oceans. If we assume Mars started with a similar ratio to Earth, which is reasonable given both planets formed from the same protoplanetary disk, then Mars must have lost 80 to 90% of its original hydrogen to space. Since most of Mars's original hydrogen was locked in water molecules, this means Mars lost the equivalent of a global ocean at least 100 to 200 meters deep on average across the entire planet. The Northern Ocean, concentrated in one hemisphere, would have been considerably deeper. But the isotopic evidence reveals something even more precise. Different measurements of deuterium to hydrogen ratios in different Martian materials show different values. Water trapped in ancient clays has a lower ratio than water in the current atmosphere, suggesting those clays formed earlier when Mars had lost less atmosphere. Water in young volcanic rocks has a higher ratio, consistent with formation more recently after more loss had occurred. Ice in the polar caps shows intermediate values. Each measurement provides a data point in time, allowing scientists to reconstruct how the deuterium to hydrogen ratio increased as Mars lost water. The story is consistent across multiple lines of evidence. Mars started wet and got progressively drier. The magnetic field measurements came from a surprising source. Mars Global Surveyor carried a magnetometer that mapped the magnetic field as it orbited the planet from 1997 to 2006. The spacecraft found no global magnetic field, as expected, but it discovered something remarkable in the ancient southern highlands. Strong localized magnetic fields embedded in the crust, preserved like fossil magnetism in rocks that formed when Mars still had an active dynamo. These magnetic signatures are organized in parallel stripes, similar to the pattern found on Earth's ocean floors where volcanic rocks recorded reversals of Earth's magnetic field over time. The Martian stripes suggest Mars once had plate tectonics, or at least some form of crustal spreading, and the rocks magnetized as they cooled in the presence of a global field. The strongest crustal fields reach intensities of 1500 nanoteslas at 400 kilometers altitude, powerful enough to create mini magnetospheres that deflect the solar wind locally. Here is what the crustal magnetic fields reveal about timing. The magnetized rocks are all ancient, dating to before about 4 billion years ago, based on crater counting and geological mapping. Younger volcanic regions show no magnetization, suggesting they formed after the global magnetic field shut off. The transition happened relatively quickly in geological terms, probably over a period of a few 100 million years, rather than gradually over billions of years. Mars's dynamo failed during the late Noachian period, right around the time the ocean was disappearing. The timing is not a coincidence. The magnetic field protected the atmosphere. When the field died, atmospheric stripping accelerated and the ocean evaporated away. Cause and effect. The detection methods for ancient water continue to improve. Spectroscopy from orbit identifies minerals that form only in water. Infrared spectrometers on Mars Reconnaissance Orbiter have mapped deposits of phyllosilicate clays, formed when volcanic rocks react with water over long periods. The clays are concentrated in the oldest terrains, particularly in the highlands south of the proposed ocean basin. Sulfate minerals which form when water evaporates appear in younger rocks, suggesting a transition from a wetter early Mars to a drier later Mars. Carbonate minerals, which should have formed abundantly if Mars had a thick carbon dioxide atmosphere and liquid water, are surprisingly rare. This carbonate mystery puzzled scientists for years. A thick carbon dioxide atmosphere should have dissolved in the ocean, forming carbonates that precipitated out and accumulated on the ocean floor. Where are they? NASA's Phoenix lander, which touched down in Mars's northern Arctic region in 2008, provided part of the answer. Phoenix dug trenches in the icy soil and analyzed the chemistry. The soil contained perchlorates, highly oxidizing salts that destroy organic molecules. If perchlorates are widespread in Martian soil, they may have also destroyed or transformed carbonates over billions of years. Or carbonates did form, but were buried beneath younger deposits, or eroded away, or remain concentrated in regions we have not yet examined closely. The mystery continues, but the absence of widespread carbonates does not disprove the ocean. It just means the chemistry was more complex than simple models predicted. The measurements converge on a consistent picture. Multiple independent lines of evidence point to the same conclusion. valley networks carved by flowing water, clay minerals formed in neutral pH water, deuterium enrichment from hydrogen escape, fossil magnetic fields that shut off around 4 billion years ago, shoreline features at consistent elevations, smooth northern plains consistent with an ancient ocean basin. Each piece of evidence has uncertainties, but together they build a case that Mars had abundant surface water in its distant past and lost it through processes we can now measure directly with spacecraft, like MAVEN. The transition from wet Mars to dry Mars was not instantaneous. The ocean likely persisted for hundreds of millions of years during the Noachian period, fed by volcanic outgassing, protected by a weakening but still present magnetic field, sustained by greenhouse warming from a thick atmosphere. As the magnetic field failed, atmospheric loss accelerated. Surface pressure dropped. The ocean began to evaporate and freeze. Some water seeped underground and froze into subsurface ice. Some was lost to space. By 3.5 billion years ago, the ocean was gone, though isolated lakes remained in crater basins and low-lying areas for millions of years longer. The transition period when Mars changed from wet to dry represents our best window for searching for signs of ancient Martian life, if it ever existed. This raises the question of how we reconstruct events that happened 4 billion years ago on another planet. The reconstruction relies on detective work, spread across centuries and decades, piecing together clues from telescopes, orbiters, landers, and rovers. The story begins in 1827 when Italian astronomer Giovanni Schiaparelli mapped Mars during a particularly close approach to Earth and reported seeing linear features he called canali, meaning channels in Italian. The word was mistranslated into English as canals, implying artificial construction, and this single mistranslation sparked decades of speculation about Martian civilization. American astronomer Percival Lowell became convinced that Mars was inhabited by an advanced but dying civilization building massive irrigation canals to transport water from polar ice caps to arid equatorial regions. He established an observatory in Flagstaff, Arizona in 1894 specifically to study Mars, and published detailed maps of the supposed canal network. Lowell's canals were an illusion, products of the human tendency to see patterns where none exist, combined with the limitations of early telescopes. But his popular books and lectures established Mars in the public imagination as a world that once had water. The first real evidence came from spectroscopy. In the epochs, Earth-based telescopes equipped with spectrometers analyze sunlight reflected from Mars to identify which wavelengths were absorbed by the Martian atmosphere. These measurements revealed that Mars's atmosphere is primarily carbon dioxide, roughly 95%, with traces of nitrogen and argon. The atmospheric pressure was estimated at only about 6 millibars, less than 1% of Earth's sea level pressure. This was shocking. At such low pressure, liquid water cannot exist on the surface except in the lowest elevations and only at temperatures near the triple point of water. The discovery of Mars' thin atmosphere made the canal hypothesis impossible and suggested the planet was a frozen desert. Early theories shifted to explain Mars as a world that had always been cold and dry. Then came Mariner 4. NASA launched the spacecraft in November 1964, and it flew past Mars on July 14, 1965, transmitting 22 images back to Earth. These were the first close-up photographs of another planet. The images showed a cratered moon-like surface with no signs of canals, no vegetation, no obvious evidence of water. Mariner 4's images were disappointing to those hoping for a vibrant world. The scientific consensus shifted further. Mars appeared dead, ancient, unchanged for billions of years. The prevailing theory held that Mars formed cold and dry and remained that way. Mariner 9 changed everything. Launched in May 1971, the spacecraft entered orbit around Mars on November 13, 1971, becoming humanity's first artificial satellite of another planet. When it arrived, a global dust storm obscured the surface, but as the storm cleared over the following weeks, Mariner 9's cameras revealed a world far more complex than Mariner 4's limited flyby images suggested. The orbiter discovered enormous volcanoes, including Olympus Mons, which rises 21 kilometers above the surrounding plains, making it the tallest volcano in the solar system. It found Valles Marineris, a canyon system stretching 4,000 kilometers across the Martian surface and reaching depths of 7 kilometers. And it found the valley networks, branching channels carved into the ancient highlands, looking exactly like river systems on Earth. These were not the straight lines Lowell imagined. These were natural drainage patterns created by flowing water. NASA's Viking program provided the next major advances. 2 identical spacecraft, Viking 1 and Viking 2, each consisting of an orbiter and a lander, launched in 1975 and arrived at Mars in 1976. Viking 1 landed in Chryse Planitia on July 20, 1976. Viking 2 landed in Utopia Planitia on September 3, 1976. Both landers carried instruments to search for signs of microbial life by analyzing soil samples for metabolic activity. The results were ambiguous and remain controversial. Some experiments showed unexpected chemical activity that could potentially be biological. Other experiments found no organic molecules, suggesting the soil was sterile. The scientific consensus eventually concluded that the Viking results did not provide convincing evidence for life, and the unexpected chemistry was likely due to reactive oxidants in the soil rather than biology. But the Viking orbiters revolutionized our understanding of Martian geology. The Viking orbiters mapped Mars at resolutions of 100 to 300 meters per pixel, revealing geological diversity that earlier missions missed. The orbiters imaged layered deposits in the polar regions, suggesting climate cycles. They photographed enormous outflow channels carved by catastrophic floods that dwarfed any floods on Earth, releasing volumes of water equivalent to the Mediterranean Sea in a matter of weeks. These outflow channels were different from the valley networks. The valley networks showed gradual erosion over long periods. The outflow channels showed sudden, violent water release, probably from subsurface aquifers that ruptured and discharged groundwater catastrophically. The Viking data suggested Mars had multiple episodes of water activity at different times and through different mechanisms. Through the ANDE, theoretical work focused on understanding how Mars could have been warm enough for liquid water despite the faint young sun. Carl Sagan and colleagues proposed in 1972 that a thick carbon dioxide atmosphere could provide sufficient greenhouse warming. But calculations showed that carbon dioxide alone was insufficient. Even with several bars of carbon dioxide pressure, equivalent to several times Earth's current atmospheric pressure, models could not raise surface temperatures above freezing on early Mars. Scientists proposed additional greenhouse gases. Water vapor amplifies warming but condenses out if temperatures drop too low. Methane is a powerful greenhouse gas, but breaks down quickly under ultraviolet light unless continuously replenished. Hydrogen was proposed in 2012 as a potential solution, with volcanic outgassing providing a steady supply. The debate continues. Mars Global Surveyor, which operated from 1997 to 2006, brought unprecedented precision to mapping Mars. The spacecraft carried a laser altimeter that measured surface elevations with vertical precision of 1 meter, creating detailed topographic maps of the entire planet. These maps revealed the dichotomy boundary, the sharp division between the low, smooth northern plains and the high, cratered southern highlands. The northern plains sit about 5 kilometers lower in elevation than the southern highlands on average. This topographic difference is enormous and requires explanation. The leading theory suggests a giant impact early in Mars' history blasted away much of the northern hemisphere's crust, creating the lowland basin. This basin would naturally collect water, which is why scientists think it became the site of the ancient ocean. Mars Global Surveyor also discovered those fossil magnetic fields in the ancient southern crust. The magnetometer data collected between 1997 and 2006 revealed magnetic field strengths and patterns that could only have formed if Mars had a global dynamo generating a magnetic field when those rocks formed and cooled. Dating the magnetized rocks based on crater counting gives ages of 4 billion years or older. The lack of magnetic signatures in younger volcanic regions indicates the dynamo shut down before 3.5 billion years ago. The timing matches the period when the ocean disappeared. The magnetic field protected the atmosphere. When the dynamo failed, the shield dropped and the atmosphere began bleeding into space. The early brought rovers to the surface. NASA's Mars exploration rovers, Spirit and Opportunity, landed in January 2004 in different locations. Spirit explored Gusev Crater, which appeared from orbit to be an ancient lake bed. Opportunity landed in Meridiani Planum, a region showing deposits of hematite, an iron oxide mineral that often forms in water. Both rovers found definitive evidence of past water. Opportunity discovered layered sedimentary rocks, with textures indicating they formed from minerals precipitating out of evaporating water. The rocks contained sphere-shaped concretions nicknamed blueberries that formed when groundwater percolated through the rock. Spirit found evidence of ancient hot springs and hydrothermal systems in the Columbia Hills. Both rovers operated far beyond their planned 90-day missions. Spirit lasted until 2010. Opportunity operated until 2018, covering 45 kilometers over 14 years. The European Space Agency's Mars Express orbiter, operating since 2003, carried ground-penetrating radar that could probe beneath the surface. In 2005, the radar detected buried deposits consistent with massive ice sheets in the mid-latitudes. In 2018, Mars Express found that 20-kilometer-wide lake of liquid water beneath the southern ice cap, confirmed through multiple radar passes showing reflections characteristic of liquid water rather than ice. The discovery demonstrated that liquid water exists on Mars today, just hidden underground where pressure and dissolved salts keep it from freezing. NASA's Phoenix lander arrived in 2008, targeting the northern Arctic region specifically to study water ice. The lander's cameras watched frost form on the surface in the Martian morning and sublimate away by afternoon. Phoenix dug trenches and exposed bright white material just beneath the surface. Time-lapse images showed this material sublimating over several days, confirming it was water ice. The ice started only 5 to 18 centimeters below the surface. Chemical analysis revealed those perchlorates, explaining why the Viking landers found no organic molecules despite them being delivered to Mars constantly by meteorites. The perchlorates oxidize organics, destroying them. Mars Science Laboratory, better known as the Curiosity rover, landed in Gale Crater in August 2012. The landing site was chosen because orbital observations showed layered deposits at the base of Mount Sharp, a 5-kilometer-high mound of sedimentary rock in the crater's center. Curiosity's instruments could analyze the chemistry and mineralogy of these layers in detail. The rover found mudstones containing clay minerals that formed in neutral pH water with low salinity. The rocks contained carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur in chemical forms usable by life. Curiosity's measurements showed that Gale Crater held a lake, possibly connected to a larger system of lakes and rivers about 3.5 billion years ago. The water persisted for millions of years, long enough to deposit hundreds of meters of sediment. This was during the late Noachian to early Hesperian period, after the ocean had vanished but when some regions still retained water. The evolution of theories about Mars over decades follows a pattern of increasing sophistication. The view of Mars as eternally frozen gave way to the recognition of past water activity. The "and" focused on understanding the greenhouse problem and the timing of climate change. The brought detailed surface chemistry and mineralogy. The confirmed liquid water persists underground and established that ancient Mars had the chemistry needed for life. Each decade added precision and nuance. The current understanding synthesizes all these discoveries. Mars formed 4.6 billion years ago from the same disk of dust and gas that created Earth. The planet differentiated into core, mantle, and crust within the first 100 million years. Volcanic activity released water and gases from the interior, building an atmosphere. A liquid outer core generated a magnetic field through dynamo action. During the Noachian period, roughly 4.1 to 3.7 billion years ago, Mars had surface water, possibly including a northern ocean, sustained by a thicker atmosphere and warmer temperatures through some combination of greenhouse gases and volcanic heat. Around 4 billion years ago, the core cooled enough that the dynamo failed and the magnetic field collapsed. Without magnetic protection, the solar wind stripped away the atmosphere over hundreds of millions of years. Surface pressure dropped. The ocean evaporated and froze. Some water was lost to space, some went underground, some locked into ice caps. By 3.5 billion years ago, the surface was mostly frozen, though isolated lakes persisted in some craters. Mars has been cold and dry for over 3 billion years. This timeline is based on crater counting, isotopic measurements, mineral identification, magnetic field patterns, and direct observations from multiple spacecraft over 5 decades. The story is remarkably consistent across different measurement techniques. But establishing that Mars had an ocean is only the beginning of understanding what that ocean means. The broader context extends far beyond one planet's lost ocean. Mars sits at a critical position in our solar system's architecture, close enough to the Sun to have received water-bearing asteroids and comets during the solar system's formation, but far enough out that it froze quickly once its atmosphere thinned. This location creates a natural experiment in planetary evolution. Venus, Earth, and Mars all formed in roughly similar ways from similar materials. All three started with water, but they followed radically different paths determined by mass, distance from the Sun, and timing. Venus became an inferno. Earth remained habitable for over 4 billion years. Mars froze. The differences teach us which factors matter most for keeping a planet alive. The mass difference drives everything. Earth's mass is 9.3 times larger than Mars. This seemingly simple ratio cascades into profound consequences. Earth's larger mass means stronger gravity, which helped our planet hold on to lighter atmospheric gases that Mars lost. It means a larger iron core with more heat content, keeping Earth's dynamo running while Mars failed. It means more intense geological activity, with plate tectonics recycling carbon between the atmosphere and rocks, regulating Earth's climate over geological time. Mars lacks plate tectonics. Its crust is a single, rigid shell. Without plate tectonics, carbon dioxide that dissolved in the ocean and formed carbonates could not be recycled back into the atmosphere through volcanic activity. This created a trap. As carbon dioxide left the atmosphere and locked into rocks, the greenhouse effect weakened, temperatures dropped, and the planet spiraled into freezing. Here is the fundamental paradox. Mars needed a thick carbon dioxide atmosphere to stay warm enough for liquid water. But liquid water removes carbon dioxide from the atmosphere by dissolving it and converting it to carbonates. On Earth, this process is balanced by plate tectonics, which subducts carbonates into the mantle where they melt and release carbon dioxide back through volcanic eruptions. The carbon cycle is a thermostat. If Earth gets too warm, more carbon dioxide dissolves in the ocean, reducing the greenhouse effect and cooling the planet. If Earth gets too cold, less carbon dioxide dissolves, the greenhouse effect strengthens, and temperatures rise. This negative feedback stabilizes Earth's climate over hundreds of millions of years. Mars lacked this stabilizer. Once the planet started cooling, there was no mechanism to reverse the trend. The cooling became runaway. The ocean froze, the atmosphere collapsed, and Mars died. The missing carbonates remain one of the great puzzles. If Mars had a thick carbon dioxide atmosphere and a large ocean for hundreds of millions of years, chemical equilibrium dictates that massive carbonate deposits should have formed. We can calculate approximately how much. An atmosphere thick enough to keep Mars warm would need pressures of at least half a bar to 2 bars of carbon dioxide. That represents a huge reservoir of carbon. When that carbon dioxide dissolved in the ocean and precipitated as carbonate minerals, it should have created deposits hundreds of meters thick across much of the ocean basin. Mars Reconnaissance Orbiter has identified some carbonate deposits from orbit, particularly in ancient rocks, dating to the Noachian period. But the total volume is far less than expected. Where did the carbonates go? Several possibilities exist. The carbonates may be buried beneath younger volcanic deposits or dust, hidden from orbital spectrometers. They may have been destroyed by acidic groundwater percolating through the rocks over billions of years. They may exist in forms we have not yet learned to detect from orbit. Or the ocean's chemistry may have been different from our assumptions. If the ocean was acidic rather than neutral or alkaline, carbonates would not have formed efficiently. Some evidence suggests early Mars may have had sulfur-rich volcanism that produced sulfuric acid, lowering ocean pH. An acidic ocean would dissolve less carbon dioxide and form fewer carbonates. This would explain the missing carbonates, but raises new questions about how an acidic ocean could have persisted and whether life could have emerged in such conditions. The measurement challenges are formidable. We are trying to reconstruct conditions on another planet 4 billion years ago using rocks that have been exposed to radiation, temperature swings, and chemical weathering for eons. Every measurement requires inferring past conditions from present clues. The valley networks tell us water flowed, but not how much or for how long. The clay minerals tell us the water was neutral pH when those specific clays formed, but not whether the entire ocean was neutral. The deuterium enrichment tells us hydrogen escaped, but calculating the original water volume requires assumptions about the starting deuterium to hydrogen ratio and the escape rate over time. Each measurement has uncertainties that compound when we try to build a complete picture. Crater counting provides relative ages but not absolute dates. The technique works by comparing the number of impact craters on different surfaces. Older surfaces have accumulated more craters. Younger surfaces have fewer. By counting craters and comparing to surfaces where we have absolute age measurements, we can estimate ages for Martian terrains. But Mars has no returned samples with radiometric dates to calibrate the crater counting curves directly. We use lunar samples and mathematical models of the impact rate in the early solar system to estimate Martian ages. The uncertainties are typically a few 100 million years for ancient surfaces. This means when we say the Noachian period ended 3.7 billion years ago, that date could be off by plus or minus 200 million years. For understanding planetary evolution, that precision is remarkable. For pinpointing exactly when the ocean disappeared, it leaves room for debate. Secondary effects complicate the story further. As Mars' atmosphere thinned, surface pressure dropped, which lowered the boiling point of water. At pressures below 6.1 millibars, the triple point of water, liquid water, becomes thermodynamically unstable. It either freezes or boils away directly to vapor, depending on temperature. Current Martian surface pressure averages about 6 millibars, but varies with elevation and season. In the deepest basins, pressure exceeds the triple point. On mountaintops, pressure drops well below it. This means as ancient Mars' atmosphere thinned, liquid water would have persisted longest in the lowest elevations, exactly where the ocean basin sits. The last remnants of the ocean would have retreated to the deepest parts before finally freezing solid. This creates a progression of environments as the planet dried. Early Noachian Mars had widespread surface water. Late Noachian Mars had isolated lakes in low-lying areas. Early Hesperian Mars was mostly frozen with occasional melting during volcanic eruptions or large impacts. This environmental diversity means different regions preserve evidence of different climate stages. The loss of water triggered climate feedbacks. Water vapor is a greenhouse gas. As water evaporated from the ocean and then escaped to space, the greenhouse effect weakened, accelerating cooling. Ice reflects more sunlight than liquid water, so as the ocean froze, Mars' albedo increased, reflecting more solar energy back to space and further cooling the planet. This is the ice albedo feedback, and it is positive, meaning it amplifies changes rather than stabilizing them. Once Mars started freezing, the feedbacks pushed it to freeze completely. The transition from habitable to frozen may have happened relatively quickly once tipping points were crossed, perhaps over just tens of millions of years, rather than the gradual decline over hundreds of millions of years that the overall timeline suggests. Our position relative to Mars provides perspective on planetary habitability. Earth sits at 1 astronomical unit from the Sun, receiving about 1,400 watts per square meter of solar energy at the top of the atmosphere. Mars sits at 1.5 astronomical units, receiving only about 600 watts per square meter. That factor of 2.3 difference in solar energy seems modest, but combined with Mars's smaller mass and lack of a long-lived magnetic field, it was enough to doom the planet to freezing. The habitable zone concept defines the range of distances from a star where a planet can maintain liquid water on its surface. For our Sun, estimates place the habitable zone's inner edge at about 0.95 astronomical units, and the outer edge at about 1.7 astronomical units. Mars sits near the outer edge. It was always marginal. Any perturbation, any loss of atmosphere, any reduction in greenhouse warming would push it over the edge into freezing. Earth's position at 1 astronomical unit places us in the middle of the habitable zone with generous margins. We can afford to lose some atmosphere or undergo moderate climate changes without crossing into runaway scenarios. Mars had no such buffer. The planet lived on the edge from the beginning. This is why planetary mass matters so critically. A Mars-mass planet at Earth's orbital distance might still lose its magnetic field and atmosphere too quickly to remain habitable. An Earth-mass planet at Mars' orbital distance might generate enough internal heat to maintain geological activity and atmospheric recycling, despite the lower solar energy. The interplay between mass and distance determines fate. The location also affected Mars' water delivery. The asteroid belt lies between Mars and Jupiter, and it contains water-rich asteroids, particularly in its outer regions. During the late heavy bombardment, roughly 4 billion years ago, gravitational interactions among the giant planets destabilized asteroid orbits, sending millions of water-bearing asteroids into the inner solar system. Earth and Mars were bombarded. Some of our ocean water may have arrived this way, delivered by asteroids after Earth's initial formation. Mars received similar deliveries, but Mars' lower gravity means impact velocities were lower, making it easier for asteroids to deliver water without vaporizing it on impact. Some models suggest Mars may have received proportionally more water from asteroids than Earth did relative to the planet's size. This could explain how Mars accumulated enough water for an ocean despite being smaller. The dichotomy between Mars' northern and southern hemispheres may also result from location and timing. The northern lowlands sit about 5 kilometers lower than the southern highlands. This creates the natural basin where the ocean would collect. But why does this dichotomy exist? The leading explanation involves a giant impact. Computer simulations show that an object roughly the size of Earth's moon, perhaps 1,000 to 2,000 kilometers in diameter, colliding with Mars at an oblique angle, could blast away the northern hemisphere's crust without destroying the planet. This impact would have occurred very early within the first 100 million years of Mars' formation, when the crust was still thin and partially molten. The basin created by this impact became the collection point for water, delivered later during the late, heavy bombardment. This connects to a broader question about planetary violence in the early solar system. Earth experienced a giant impact that created our moon roughly 4.5 billion years ago when an object the size of Mars struck the proto-Earth. Venus may have experienced an impact that flipped its rotation, which is why Venus spins backward compared to other planets. Mercury's large iron core relative to its mantle suggests it was once larger but lost its outer layers in a collision. The early solar system was chaotic. Planets migrated. Orbits crossed. Collisions reshaped worlds. Mars' northern basin is evidence of this violence. The impact that created it determined where the ocean would later form, which influenced where we look for signs of ancient life today. Why this matters comes down to understanding how common, habitable environments are in the universe. Mars was habitable. For hundreds of millions of years, possibly longer, the planet had liquid water on its surface and the chemical ingredients for life. If life emerged on Mars during that window, then we have two independent origins of life in one solar system. That would suggest life emerges readily wherever conditions permit. If life did not emerge on Mars despite favorable conditions lasting hundreds of millions of years, then life may require conditions more specific or timescales longer than we currently understand. Either answer transforms our view of biology's place in the cosmos. The story of Mars's ocean is ultimately about fragility and the narrow requirements for maintaining habitability over billions of years. Having water is not enough. Having the right chemistry is not enough. A planet needs mass sufficient to generate internal heat, maintain geological activity, and hold an atmosphere. It needs a magnetic field to shield against stellar wind. It needs mechanisms to stabilize climate over time. It needs to form in the right location. Mars had water but lacked the staying power to keep it. And the question becomes whether Mars was ever truly alive in the biological sense, or whether it died before life could emerge. The central debate about Mars' ancient climate divides scientists into two camps with fundamentally different interpretations of the same evidence. Both groups agree Mars had substantial surface water 4 billion years ago. Both agree the planet lost that water, but they disagree profoundly about the climate conditions under which the water existed. One camp argues for a warm and wet Mars with temperatures consistently above freezing, rain falling from clouds, rivers flowing year-round, and an ocean that persisted as liquid water for hundreds of millions of years. The other camp argues for a cold and icy Mars where surface temperatures remained below freezing most of the time. Water existed primarily as ice, and liquid water appeared only during brief warm periods triggered by volcanic eruptions, asteroid impacts, or orbital variations. This is not a minor disagreement about details. It represents completely different visions of early Mars and requires different explanations for how the valley networks formed. The warm and wet hypothesis relies primarily on climate modeling. Researchers build computer simulations of Mars' early atmosphere, incorporating what we know about solar luminosity 4 billion years ago. Mars's orbital parameters, surface composition, and potential greenhouse gases. They input different atmospheric compositions and pressures, then calculate whether the resulting temperatures allow liquid water to exist on the surface. The models consistently show a problem. With only carbon dioxide as a greenhouse gas, even thick atmospheres fail to warm Mars above freezing. Simulations using 300 to 600 millibars of carbon dioxide pressure, roughly half to equal Earth's current atmospheric pressure, produce global average temperatures of -40 to -60 degrees Celsius. That is far too cold for liquid water. To solve this, researchers have proposed additional greenhouse gases. Water vapor amplifies warming created by carbon dioxide, but water vapor condenses and rains out if temperatures drop below freezing, creating a catch-22. You need warmth to keep water vapor in the atmosphere, but you need water vapor to create warmth. Methane is a powerful greenhouse gas, but it photodissociates rapidly under ultraviolet light, breaking apart within a few hundred years unless continuously replenished by volcanic activity or biological processes. Hydrogen has emerged as a leading candidate. In 2012, researchers showed that volcanic outgassing could maintain hydrogen concentrations of a few percent in the atmosphere, and hydrogen combined with carbon dioxide creates collision-induced absorption that dramatically enhances the greenhouse effect. Models using 2 to 5% atmospheric hydrogen can warm early Mars above freezing, but this requires sustained volcanic activity to replenish the hydrogen continuously. The warm and wet camp points to the valley networks as their strongest evidence. These drainage systems look exactly like rain-fed river networks on Earth, with tributary patterns that suggest gradual erosion over millions of years. Rainfall requires atmospheric cycling with evaporation, cloud formation, precipitation, and runoff. That requires sustained warm temperatures. Computer models of valley network formation show that creating the observed channel depths and widths requires water flow over at least tens of millions of years. Flash floods or episodic melting cannot carve these features. They need persistent flow. The morphology argues for a water cycle, which argues for a warm climate. Mineralogical evidence supports this interpretation. Phyllosilicate clays found in Noachian age rocks form through prolonged weathering of volcanic rocks in the presence of liquid water at neutral pH. Laboratory experiments show this weathering process requires thousands to millions of years of continuous water-rock interaction. The clays are widespread across the ancient highlands, suggesting water was available across large areas for extended periods. Carbonate minerals, though less abundant than expected, do exist in some Noachian rocks, indicating that liquid water interacted with carbon dioxide from the atmosphere. The warm and wet scenario naturally explains all these observations. Mars had a thick atmosphere. Greenhouse warming kept temperatures above freezing, rain fell, rivers flowed, and the ocean persisted as a permanent feature for hundreds of millions of years during the Noachian period. But here is where the cold and icy hypothesis pushes back with equally compelling evidence. Researchers in this camp argue that the geological features attributed to warm conditions can form under cold conditions through different mechanisms. ice sheets flowing downhill under their own weight can carve valleys. Subglacial water flowing at the base of glaciers erodes channels. Periodic melting during volcanic eruptions or large asteroid impacts releases water that flows briefly before refreezing. The valley networks may have formed through thousands of episodic melting events over hundreds of millions of years, rather than through continuous rainfall. The cold scenario also solves the greenhouse problem by eliminating it. If Mars was mostly frozen, you do not need to explain how it stayed warm enough for liquid water, because it did not. The cold and icy camp points to specific features that seem inconsistent with a warm climate. Many Noachian Age valley networks show characteristics more similar to glacial valleys than river valleys. They have U-shaped cross-sections rather than V-shaped profiles. They lack extensive floodplains or delta deposits at their terminations that you would expect from long-lived rivers. Some valleys appear to start at specific elevations on crater walls or mountain slopes, consistent with melting at particular elevations rather than rainfall-driven erosion. Computer simulations of glacial flow show that ice sheets hundreds of meters thick covering the ancient highlands can reproduce many of the observed valley features through basal melting and ice flow. The mineralogical evidence also admits cold interpretations. Phyllosilicate clays can form through hydrothermal alteration in volcanic regions, where hot rocks interact with liquid water underground without requiring a warm surface climate. Groundwater percolating through volcanic deposits can create clays even if the surface is frozen. The clay distribution shows concentrations in volcanic regions and impact craters, consistent with localized heating rather than global surface weathering. Some of the most abundant clays detected from orbit are iron and magnesium-rich smectites that form efficiently in hydrothermal systems on Earth. The cold scenario suggests Mars had extensive subsurface liquid water in volcanic and impact-heated regions while the surface remained frozen. Recent analysis of Martian meteorites provides another line of evidence favoring cold conditions. These rocks, blasted from Mars by asteroid impacts and eventually falling to Earth, preserve ancient Martian water trapped in minerals. Oxygen isotope measurements of this water reveal temperatures at which the water-rock interactions occurred. Multiple studies published between 2015 and 2020 found formation temperatures of 0 to 20 degrees Celsius for Noachian Age samples, cooler than expected for a warm and wet climate, but consistent with occasional melting. The meteorite evidence suggests Mars experienced near-freezing conditions, not the warm tropical or temperate climate the warm and wet hypothesis requires. The disagreement extends to atmospheric evolution models. Warm and wet scenarios require Mars to have had atmospheric pressure of at least half a bar, perhaps as high as 2 bars, during the Noachian period. That atmosphere would have contained hundreds of millibars of carbon dioxide, plus whatever additional greenhouse gases provided the extra warming. Losing that much atmosphere to space requires extremely high escape rates, perhaps 10 to 100 times higher than MAVEN currently measures even during solar storms. The numbers are challenging. Can the solar wind really strip away that much gas over several 100 million years? Models disagree. Some simulations show it is possible if the young sun's activity was sufficiently intense. Others suggest the required escape rates are too high to be realistic. Cold and icy scenarios require less atmosphere. If most water existed as ice with only episodic melting, surface pressure could have been lower, perhaps 100 to 300 millibars. Less atmosphere means less needs to be lost to reach current conditions. The escape problem becomes less severe, but these lower pressures make warming even more difficult, strengthening the case that Mars was cold rather than warm. The logic becomes circular. If Mars was warm, it needed thick atmosphere, but thick atmosphere is hard to lose. If Mars was cold, it needed less atmosphere, which is easier to lose, but that makes warming impossible. The statistical significance of this debate shows up in published literature. A 2016 review of Mars climate modeling papers found that approximately 60% of climate models fail to produce sustained above-freezing temperatures, even with optimistic assumptions about greenhouse gases. About 30% can achieve intermittent warming through episodic mechanisms like volcanism or orbital variations. Only about 10% of models can maintain continuously warm conditions, and those require specific combinations of atmospheric composition and surface properties that may or may not be realistic. The models that succeed in warming Mars typically require precise fine-tuning of parameters. Small changes in assumptions produce frozen planets. This fragility suggests Mars may have been at the edge of habitability, with climate hovering near the freezing point rather than being comfortably warm. Observational campaigns trying to resolve the debate have produced mixed results. In 2015, researchers used crater statistics to estimate how long valley networks were actively forming. They counted small impact craters superimposed on valley networks. Fewer craters means younger surface, suggesting recent activity. The results indicated valley network formation occurred sporadically over hundreds of millions of years, with long dormant periods between active phases. This pattern fits cold and icy scenarios with episodic melting better than warm and wet scenarios with continuous rainfall. But in 2017, different researchers analyzing the same data with different statistical methods concluded that valley network formation clustered in a relatively brief period during the late Noachian, suggesting intense fluvial activity over tens of millions of years, more consistent with warm and wet conditions. The data supports both interpretations depending on analytical assumptions. Why this matters extends beyond academic debate. The warm versus cold question determines what environments would have been available for potential Martian life. Warm and wet Mars provides stable, long-lasting aquatic environments where life could emerge and evolve over hundreds of millions of years. Complex organic chemistry flourishes in liquid water. Energy sources abound in sunlit, shallow oceans and river deltas. Life could spread across the planet through interconnected water systems. This is the optimistic scenario for Martian biology. Cold and icy Mars offers scattered temporary habitats in volcanic hot springs, impact crater lakes, and subglacial environments. These habitats appear and disappear on timescales of thousands to millions of years. Life would need to emerge quickly, adapt to harsh conditions, and survive repeated freezing. This is the pessimistic scenario where Martian life faces constant extinction pressure. The stakes involve how we search for evidence of ancient life. If Mars was warm and wet, we should look for fossils or biosignatures in sedimentary rocks deposited in lakes and shallow marine environments. River deltas where water carried organic material and concentrated it in layers would be prime targets. The smooth northern plains that may have been the ocean floor could contain microfossils preserved in mudstone. If Mars was cold and icy, we should focus on hydrothermal deposits in volcanic regions or impact craters where heat created temporary oases. We should look for life that survived in extreme conditions similar to Earth's deep subsurface or Antarctic ice ecosystems. The search strategies are fundamentally different. The tension also affects models of planetary habitability beyond Mars. If we cannot determine whether Mars was warm or cold 4 billion years ago, despite having spacecraft orbiting the planet, analyzing its rocks, measuring its atmosphere, and mapping its surface in exquisite detail, how can we possibly determine whether exoplanets orbiting distant stars are habitable? We can measure an exoplanet's size, mass, and distance from its star. We can sometimes detect atmospheric composition through transit spectroscopy, but we cannot see surface features or sample rocks. If Mars with all its data remains ambiguous, exoplanet habitability assessments are even more uncertain. The warm versus cold Mars debate reveals how many factors influence climate and how difficult it is to reconstruct past conditions even with substantial data. Recent missions have not resolved the debate, but have added nuance. NASA's InSight lander, which operated from 2018 to 2022, measured Mars' internal structure using seismology. The data revealed that Mars' crust is thinner than many models predicted, perhaps 20 to 70 kilometers thick in the northern lowlands. A thin crust means heat from the interior could reach the surface more easily, supporting more vigorous volcanic activity in the past. That strengthens arguments for volcanism, providing episodic heating in cold scenarios, or sustained greenhouse gas replenishment in warm scenarios. InSight also detected Marsquakes associated with volcanic regions, indicating Mars' interior is still partially molten. The planet is not completely dead geologically, but the seismic data cannot tell us what Mars' climate was like 4 billion years ago. The European Space Agency's ExoMars Trace Gas Orbiter has been analysing Mars's atmospheric composition in unprecedented detail since 2016. The spacecraft detected no methane in most measurements, contradicting earlier ground-based and orbital detections that suggested sporadic methane releases. If methane exists, its concentrations are extremely low and variable. This undermines scenarios where methane contributed to greenhouse warming in the past, unless methane behavior was completely different 4 billion years ago. The Trace Gas Orbiter did detect hydrogen chloride gas appearing seasonally, the first time this molecule has been found in Mars's atmosphere. The hydrogen chloride likely comes from volcanic outgassing or reactions involving perchlorates in dust. Its presence shows Mars's atmospheric chemistry is more active than expected, with ongoing exchanges between surface and atmosphere. The debate continues because both warm and wet and cold and icy scenarios can explain large portions of the evidence. Neither can explain everything. This suggests the truth may be more complex than either pure scenario. Perhaps Mars oscillated between warm and cold states driven by orbital variations, volcanic activity, and asteroid impacts. Perhaps different regions experienced different climates simultaneously, with the northern ocean remaining liquid while the southern highlands were frozen. Perhaps the early Noachian was genuinely warm for tens of millions of years, before transitioning to colder conditions with episodic melting. The measurements we need to resolve this debate require returned samples analysed in Earth laboratories and human explorers investigating sites with their own eyes and hands. Until then, the warm versus cold question remains open, with profound implications for understanding how Mars lost its ocean and whether that ocean ever hosted life. The counterintuitive reality is that Mars was most habitable when the Sun was least helpful. 4 billion years ago, during the Noachian period when Mars had its ocean, the Sun shone 25 to 30% dimmer than it does today. Young stars of the Sun's type are cooler and less luminous because they have not yet built up the helium ash in their cores that increases fusion efficiency over time. The faint young sun paradox affects Earth too. Our planet should have been frozen solid in its first billion years, yet geological evidence shows liquid water existed on Earth at least 3.8 billion years ago. For Mars, located 50% farther from the Sun, the problem is even more severe. The planet received only about 40% of the solar energy Earth received, and Earth itself was receiving less than today. By all rights, Mars should have been a frozen wasteland from birth, yet it had flowing rivers and possibly an ocean. The planet was warm when it should have been coldest. This seems backwards until you understand what really mattered was not solar energy, but internal heat and atmospheric insulation. Mars was geologically active in its youth. The planet's interior was fully molten. Radioactive elements decayed, rapidly releasing heat. Volcanic eruptions were frequent and massive. Olympus Mons and the other Tharsis volcanoes began forming during the Noachian period, pumping enormous quantities of water vapor, carbon dioxide, sulfur dioxide, and possibly hydrogen into the atmosphere. This volcanic outgassing built Mars' atmosphere from the inside, independent of solar heating. The faint sun actually helped in one way. Less ultraviolet radiation meant greenhouse gases like methane and hydrogen broke down more slowly, staying in the atmosphere longer. The weak young sun was not the problem. The problem was Mars's size, which determined how long geological activity could sustain atmospheric replenishment. The chain of causation runs opposite to intuition. You might think Mars lost its ocean because the planet was too cold. But Mars lost its ocean because the planet was too small. Small planets cool faster. Mars' core solidified. The magnetic field collapsed. The solar wind stripped the atmosphere. Surface pressure dropped. Water became unstable and evaporated or froze. Temperature was a consequence, not a cause. The real killer was thermal evolution driven by the planet's volume to surface area ratio. This is thermodynamics playing out over billions of years. Heat loss is proportional to surface area. Heat content is proportional to volume. As size decreases, the ratio shifts against heat retention. A planet half Earth's diameter has 1/8 the volume, but 1/4 the surface area. It cools 4 times faster per unit volume. Mars is roughly half Earth's diameter. The planet never had a chance to maintain internal heat for billions of years. Here is a useful analogy. Imagine 2 cups of coffee, one large and one small, both starting at the same temperature. The small cup cools to room temperature faster because it has more surface area per unit volume. Heat escapes through the surface. The larger cup stays warm longer because it has more thermal mass relative to its cooling surface. This exact principle determines planetary lifetime. Mars is the small cup. Earth is the large cup. Both started hot. Mars cooled in a few 100 million years. Earth is still cooling after 4.5 billion years and will remain geologically active for billions more. The ocean on Mars existed during the planet's brief hot youth. When that youth ended, the ocean died with it. The observational evidence for this counterintuitive story comes from the magnetic field measurements. Mars Global Surveyor's magnetometer found strong crustal magnetic fields only in ancient terrains dating to before 4 billion years ago. Younger volcanic regions show no magnetization. This creates a binary division. Old rocks are magnetized. Young rocks are not. The transition is sharp, occurring over a geological instant, probably a few 100 million years at most. This tells us the magnetic field did not gradually weaken. It shut off relatively quickly once the core began solidifying. The dying magnetic field could not maintain a stable configuration. It weakened, became unstable, reversed polarity chaotically, then failed entirely. The crustal stripes showing magnetic reversals are fossils of those final chaotic reversals before the dynamo died. Computer simulations of planetary core evolution reproduce this pattern, but with a twist. The models show that a Mars-sized planet should maintain a magnetic field for approximately 500 million to 1 billion years after formation, depending on initial heat content and core composition. This matches the observations. Mars formed 4.6 billion years ago. The magnetic field died around 4 billion years ago. 600 million years of dynamo activity. The twist is that even small changes in initial conditions produce large changes in magnetic field lifetime. A Mars with 5% more mass might have maintained its field for an additional 200 million years. A Mars with 5% less mass might have lost its field 200 million years earlier. The boundary is sharp. Just below a critical mass threshold, planetary dynamos fail quickly. Just above that threshold, they persist for billions of years. Mars formed just below the threshold. This creates statistical improbability in the timing. Mars' magnetic field died right around the same time the late heavy bombardment was occurring, roughly 4.1 to 3.8 billion years ago. The late heavy bombardment was a period when gravitational interactions among the giant planets destabilized asteroid orbits, sending a surge of impacts throughout the inner solar system. Earth's moon preserves evidence of this bombardment in its heavily cratered highlands. Mars was bombarded simultaneously. Large impacts can inject huge amounts of water vapor and dust into the atmosphere, temporarily warming the climate even without a magnetic field. Some researchers have proposed that the late heavy bombardment extended Mars' warm period beyond what the magnetic field lifetime alone would allow. Each giant impact created a temporary greenhouse effect lasting thousands of years. Hundreds or thousands of impacts over a few 100 million years could have provided episodic warming that kept liquid water flowing intermittently, even as the magnetic field failed and atmospheric stripping accelerated. The timing was either coincidence or causally connected in ways we do not yet understand. Alternative theoretical frameworks have emerged to explain Mars without requiring a warm climate. The cryosphere hypothesis suggests Mars has always been cold, but has vast reserves of subsurface ice that occasionally melt when heated by volcanism or impacts. In this model, the valley networks formed when volcanic heat melted subsurface ice, and the liquid water flowed at the surface briefly before refreezing. The ocean basin never contained a permanent ocean, but was repeatedly flooded by catastrophic releases from melting permafrost. Each flood would last years to centuries before freezing solid again. Over hundreds of millions of years, thousands of these episodic floods could carve the observed valley networks and smooth the northern plains without ever requiring sustained warm conditions. This cryosphere model solves several problems. It explains the valley networks without needing greenhouse warming. It explains why we do not find abundant carbonates, because liquid water was never present long enough for massive carbonate precipitation. It explains the transition from wet to dry Mars as simply the end of volcanic heating sufficient to melt permafrost rather than a catastrophic climate collapse. The model is testable. If correct, we should find evidence of flash flooding rather than gradual erosion in the valley networks. We should find ice-related features like patterned ground and polygonal terrain dating to the Noachian period. We should find volcanic centers spatially associated with valley network formation. Some of this evidence exists, but it is not conclusive. Modified greenhouse theories try to make warm Mars work by invoking mechanisms we can barely measure. One proposal suggests that impacts during the late heavy bombardment created temporary oceans by melting subsurface ice and generating thick water vapor atmospheres that persisted for millions of years after each impact. A sufficiently large impact, say from an asteroid 100 kilometers in diameter, could melt enough ice to create a temporary ocean covering much of the northern lowlands. The water vapor atmosphere would provide intense greenhouse warming. The ocean would last until the water refroze or escaped to space, perhaps 10 million years. Then, another impact would repeat the process. In this episodic ocean model, Mars had liquid water on the surface for a total of perhaps 100 million years. spread across the Noachian period, but never continuously. Life could emerge in these temporary oceans, but would face repeated extinction events when the oceans froze. Another modified theory proposes that Mars' atmosphere was much dustier in the past than today. Dust in the atmosphere creates an anti-greenhouse effect during the day by reflecting sunlight, but provides an infrared blanket at night, slowing heat loss. If Mars's atmosphere contained enough dust suspended by stronger winds, driven by a thicker atmosphere, the dust could have warmed nighttime temperatures above freezing, even if daytime temperatures remained cold. This would allow liquid water to persist in equatorial regions, where daytime heating was sufficient. The valley networks concentrate in equatorial to mid-latitude regions, consistent with this prediction. But maintaining high dust loads requires strong winds, which requires thick atmosphere, which returns us to the greenhouse problem. The statistical distribution of valley networks provides another counterintuitive clue. Detailed mapping shows the networks are not uniformly distributed across Mars. They concentrate in the ancient southern highlands, but avoid the smooth northern plains. They cluster around volcanic regions, particularly the Tharsis Rise and the rim of the Hellas Impact Basin. This distribution suggests valley formation was controlled by specific geological contexts rather than global climate. If Mars had a warm, wet climate with global rainfall, valleys should form everywhere with sufficient topographic relief. The observed clustering suggests localized heat sources, volcanic or impact-related, controlled where liquid water could exist. This argues against warm and wet Mars and favors episodic melting scenarios. Yet other evidence pulls in the opposite direction. Phyllosilicate clays are found across wide areas of the ancient highlands, not just near volcanic centers. If water-rock interactions occurred only in localized volcanic hydrothermal systems, the clays should cluster near volcanoes. Instead, they appear regionally over areas spanning millions of square kilometers. This suggests water was available across large regions, either from rainfall or from a high groundwater table that intersected the surface widely. The clay distribution argues for warm and wet Mars. The evidence genuinely pulls both ways. Recent discoveries add complexity. In 2019, researchers analyzing high-resolution images from Mars, Reconnaissance Orbiter found features that look like ancient river deltas preserved in craters. River deltas form when rivers flow into standing bodies of water, like lakes or oceans. The sediment carried by the river spreads out in fan-shaped deposits as the water velocity drops. These deltas require sustained water flow, not brief flooding. The Jezero Crater Delta, where NASA's Perseverance rover is currently exploring, shows clear evidence of multiple episodes of sediment deposition, suggesting the river flowed into the crater lake repeatedly over long periods. This argues for climate stability, not catastrophic episodic flooding. But how many deltas is enough to prove a point? Researchers have identified roughly 200 crater lakes with potential delta deposits. Is that a lot or a little? Mars has hundreds of thousands of craters. If only a tiny fraction contained deltas, that suggests lakes and rivers were rare, special cases associated with local heat sources. If 200 seems like a lot, that suggests widespread water activity requiring a warm climate. The truth likely involves elements of both scenarios operating at different times or in different regions. Early Noachian Mars might have been warm enough for sustained surface water for several tens of millions of years, when volcanic activity peaked and the magnetic field was strongest. Late Noachian Mars was probably cold with episodic melting. The transition was gradual, with climate becoming increasingly harsh over hundreds of millions of years. This hybrid scenario explains the full range of evidence better than either pure scenario alone. but it also makes the story more complex and harder to test. The modified theories and alternative frameworks proliferate because the available data underdetermine the answer. We have enough evidence to rule out some extreme scenarios. Mars definitely was not completely dry. Mars probably was not continuously warm and wet for 1 billion years. But within those bounds, many different climate histories remain plausible. Future missions carrying different instruments will narrow the possibilities. Ground-penetrating radar that can map subsurface ice deposits will test cryosphere models. Drilling into clay-rich rocks and analyzing the minerals in detail will reveal formation temperatures and timescales. Seismic networks that run for years will map Mars' internal structure and constrain heat flow. Each new measurement constrains the possibilities. The counterintuitive aspects of Mars' story reveal how planets work in ways that violate common sense. Habitability depends more on interior heat than sunlight. Magnetic fields matter more than we realized. Planetary mass determines destiny across billions of years. The ocean existed when it should not have and disappeared when it should have persisted. Everything about Mars seems backwards until you understand the physics, and that physics can be measured with instruments sensitive enough to read the planet's history written in atoms. The measurement of deuterium to hydrogen ratios in Mars' atmo-hydrogen ratios in Mars' atmosphere represents one of the most precise detective techniques available for reconstructing the planet's water loss. The method relies on the fact that deuterium, heavy hydrogen with 1 proton and 1 neutron, behaves almost identically to normal hydrogen chemically, but escapes to space much more slowly because it is twice as heavy. When hydrogen atoms in the upper atmosphere gain enough energy to reach escape velocity, normal hydrogen with mass of 1 atomic unit escapes preferentially over deuterium with mass of 2 atomic units. This process is called mass fractionation, and it gradually enriches the remaining atmosphere in the heavier isotope. By measuring how much enrichment has occurred, scientists can calculate how much hydrogen Mars has lost. NASA's Curiosity rover performed the most precise deuterium measurements to date using its sample analysis at Mars instrument, known as SAM. Between 2012 and 2015, SAM analyzed atmospheric gases and water extracted from rock samples at different locations in Gale Crater. The tunable laser spectrometer inside SAM measured the absorption of infrared light by water molecules containing normal hydrogen versus deuterium. The measurements revealed a deuterium to hydrogen ratio of about 7.3 times higher than Earth's ocean water, with precision of plus or minus 10%. Earlier measurements from Earth-based telescopes and Mars Express found ratios of 5 to 6 times Earth's value, slightly lower but consistent within uncertainties. The variation suggests the atmosphere is not perfectly mixed, or that different reservoirs of water on Mars experience different degrees of loss. Ground-based telescopes measure atmospheric deuterium by analyzing sunlight reflected from Mars. The Keck Observatory in Hawaii, using its high-resolution spectrograph, detected absorption lines from both normal water vapor and heavy water vapor containing deuterium in Mars' atmosphere in observations from 1988 through 2014. These measurements track how the ratio changes with season and location. The data show the northern polar region has slightly higher deuterium enrichment than equatorial regions, suggesting the polar ice caps preserve water that has been fractionated longer. The measurements require extraordinarily precise wavelength calibration because the spectral lines from normal and heavy water are very close together, separated by only a few hundredths of a nanometer in wavelength. Observing these tiny differences through Earth's turbulent atmosphere pushes ground-based spectroscopy to its limits. Mars Express, orbiting since 2003, carries a spectrometer called SPECAM that measures atmospheric composition, by observing how starlight passes through Mars' atmosphere when stars rise or set as seen from the spacecraft. This stellar occultation technique provides vertical profiles of atmospheric constituents at different altitudes. SPICARM detected water vapor, carbon dioxide, and ozone by comparing absorption at wavelengths specific to normal versus heavy water. The instrument measured deuterium enrichment at altitudes from 20 to 100 kilometers above the surface. The measurements revealed that deuterium enrichment increases with altitude, exactly as expected if lighter hydrogen is escaping from the top of the atmosphere, while heavier deuterium accumulates below. This altitude profile confirms the escape mechanism and validates the overall loss calculations. The characteristic timescale for hydrogen escape can be derived from these measurements. Current escape rates measured by MAVEN are about 50 to 100 grams per second of hydrogen. At this rate, Mars would need about 100 million years to lose the equivalent of Earth's Arctic Ocean, assuming all the water was converted to hydrogen and lost. But the deuterium enrichment of 5 to 8 times suggests Mars has lost much more than one Arctic Ocean worth of water. The math works if escape rates were much higher in the past, or if some water was lost through other mechanisms like impact erosion. Large asteroid impacts can blast atmosphere into space directly without requiring atom-by-atom escape. Computer models combining gradual escape with episodic impact erosion can account for the observed deuterium enrichment over Mars' 4 billion-year history. Independent confirmation of water loss comes from studying Martian meteorites. About 200 meteorites found on Earth have been identified as originating from Mars, blasted off the planet by large impacts. These rocks preserve samples of Martian material, including tiny amounts of water trapped in minerals. Scientists measure oxygen isotope ratios in this water to determine formation temperatures and hydrogen isotope ratios to measure fractionation. A 2015 study of the meteorite Northwest Africa 7234, nicknamed Black Beauty, found deuterium to hydrogen ratios in different minerals ranging from 2 to 5 times Earth's value. The variation indicates different minerals formed at different times in Mars' history, sampling water reservoirs that had experienced different amounts of fractionation. Older minerals have less enrichment, consistent with formation when Mars had lost less hydrogen. Younger minerals show more enrichment. The meteorite record provides time-stamped samples spanning billions of years. The precision of these measurements has improved dramatically over decades. In the EU, Viking landers measured atmospheric composition but could not detect deuterium. The instruments lacked sufficient mass resolution to distinguish hydrogen at mass 1 from deuterium at mass 2. In the EU, ground-based telescopes achieved the first detections but with uncertainties of 50% or more. They brought infrared spectrometers with higher resolution, reducing uncertainties to 20 to 30%. The SOAR Mars Express and ground-based observations push precision to 10 to 15%. Curiosity's SAM instrument in the achieved 5 to 10% precision. Future missions plan mass spectrometers with precision better than 1%, allowing detection of small temporal variations that could reveal seasonal cycling or ongoing escape processes. Radar measurements probe beneath Mars' surface to find ice and liquid water hidden from optical instruments. Mars Express carries MARSIS, the Mars Advanced Radar, for subsurface and ionosphere sounding, which has been operating since 2005. MARSIS transmits radio waves at frequencies between 1.3 and 5.5 MHz toward Mars's surface. These waves penetrate through ice and dry rock up to several kilometers deep. When the radar encounters boundaries between materials with different electrical properties, some of the energy reflects back to the spacecraft. By measuring the time delay of these reflections and their strength, scientists map subsurface structure. The technique works because ice, liquid water, rock, and dust have different dielectric constants that determine how radar waves propagate through them. Ice is nearly transparent to radar at Mars's frequencies. Dry rock partially absorbs and scatters radar. Liquid water strongly reflects radar and creates bright echoes. In 2018, researchers analyzing Mars's data from the South Polar region found a bright reflection about 1.5 kilometers beneath the ice surface, spanning roughly 20 kilometers in width. The reflection characteristics matched liquid water much better than ice or rock. The strength of the reflection, its sharpness, and its constant elevation across the detection area all indicated a layer of liquid water beneath the ice cap. The discovery was controversial because temperatures at that depth should be minus 68 degrees Celsius, well below water's freezing point. The liquid must contain dissolved salts that lower the freezing point, creating a briny lake similar to subglacial lakes beneath Antarctica's ice. Subsequent analysis between 2018 and 2022 using higher resolution processing techniques found additional bright reflections suggesting multiple pockets of liquid water scattered beneath the south polar layered deposits. The total area potentially containing subsurface liquid water covers several thousand square kilometers. However, some scientists argue the bright reflections could be explained by clays or hydrated salts, rather than liquid water. The debate continues, with new data processing methods being applied to distinguish between possibilities. Mars's subsurface remains largely unexplored. Mars can only detect features larger than a few kilometers across. Smaller pockets of liquid water or ice deposits could exist undetected. Future radar instruments will operate at higher frequencies with better resolution. The European Space Agency's planned PRIME mission, proposed for launch in the early this year, would carry a ground-penetrating radar operating at frequencies up to 50 MHz, providing resolution of tens of meters rather than kilometers. This would allow mapping of ice layers, buried channels, and potential subsurface water reservoirs in unprecedented detail. The Chinese Tianwen-3 mission, planned for the late afternoon, will include ground-penetrating radar on its rover to search for subsurface ice at its landing site. These future missions will test hypotheses about subsurface water distribution that current instruments cannot resolve. Imaging from orbit has improved from resolutions of hundreds of meters per pixel to 25 centimeters per pixel today. Mars Reconnaissance Orbiter's high-rise camera, operating since 2006, can resolve features the size of a desk from orbit 300 kilometers above Mars. This resolution allows detailed study of surface textures, layering in exposed cliffs and morphological features that constrain formation processes. High-rise images have revealed recurring slope lineae, dark streaks that appear on steep slopes during warm seasons and fade during cold seasons. These features were initially interpreted as evidence of flowing briny water, but recent studies suggest they form through dry granular flows without requiring liquid water. The debate illustrates how even high-resolution imaging can be ambiguous without ground truth. The extraction of information from images relies on photoclinometry, stereo imaging, and spectral analysis. Photoclinometry uses shadows and surface brightness variations to calculate slopes and surface roughness. Stereo imaging from multiple viewing angles allows construction of three-dimensional topographic models with vertical precision of about 1 meter. Mars Reconnaissance Orbiter's context camera and HiRISE work together to provide stereo coverage of selected areas. Scientists have built digital terrain models of proposed landing sites, valley networks, polar layered deposits, and other features of interest. These models reveal fine-scale topography that constrains how water flowed across the surface. Spectroscopy from orbit identifies minerals by their absorption features at specific wavelengths. Mars Reconnaissance Orbiter's CRISM spectrometer measures reflected sunlight from 400 to 4,000 nanometers wavelength, with spectral resolution fine enough to distinguish different clay minerals, sulfates, carbonates, and other hydrated minerals. CRISM data showed that phyllosilicate clays are widespread in Noachian age terrains, but rare in younger rocks, providing key evidence for the transition from wet early Mars to dry later Mars. The instrument can detect minerals in deposits as small as 18 meters across from orbit. Targeting CRISM observations to specific locations identified through imaging allows detailed mineralogical mapping. In situ analysis by rovers provides ground truth that orbital observations cannot match. Curiosity's Chi-Min instrument is an X-ray diffractometer that precisely identifies minerals by their crystal structure. The rover drills into rocks, extracts powder, and delivers it to Chi-Min, which shoots X-rays through the sample. The diffraction pattern reveals which minerals are present and in what proportions. Chi-Min measurements in Gale Crater found mudstones containing 20 to 30% phyllosilicate clays, primarily smectites. The analysis confirmed that these rocks formed in a lake environment with neutral pH water, not just hydrothermal alteration. The precision of Chi-Min's mineral identification exceeds what orbital spectrometers can achieve, but the rover can only sample a tiny fraction of Mars' surface. Future observations will combine orbital, aerial, and surface measurements. NASA's Perseverance rover is collecting samples for eventual return to Earth, where laboratory instruments can perform analyses impossible on Mars. Mass spectrometers on Earth can measure isotope ratios with precision of parts per million. Electron microscopes can search for microfossils at nanometer scales. Organic chemistry laboratories can detect and identify complex molecules at concentrations of parts per billion. The Mars Sample Return mission, planned for the early to mid-2020, will bring back about 30 samples collected by Perseverance from Jezero Crater. These samples will include sedimentary rocks from the ancient river delta, potentially preserving organic molecules or biosignatures if life ever existed in the crater lake. The Ingenuity helicopter demonstrated in 2021 that powered flight works in Mars' thin atmosphere. Future missions could deploy larger helicopters or fixed-wing aircraft to survey wide areas at resolutions intermediate between rovers and orbiters. An aerial vehicle could cover hundreds of kilometers, far more than a rover, while maintaining resolution of a few centimeters. This would allow detailed surveys of valley networks, channel systems, and potential landing sites for human missions. The European Space Agency has proposed a Mars Aerobot, a balloon-based platform that could drift with winds while taking measurements, covering thousands of kilometers over weeks or months. The characteristic scales these instruments measure span 14 orders of magnitude. Orbital spectrometers detect mineral deposits meters across. Rovers analyze grains microns in size. Return samples will be examined at nanometer scales. The vertical scale ranges from Mars' deep interior, probed by seismology to depths of 2,000 kilometers, to the upper atmosphere at 500 kilometers altitude, where MAVEN measures escape processes. The temporal scales span from millisecond measurements of atmospheric density, fluctuations to isotopic records integrated over billions of years. Each measurement technique provides a different window into Mars' history, and combining them creates a multi-dimensional picture. The instruments revealing Mars' lost ocean required decades of development and billions of dollars of investment, but they work. The measurements converge on consistent answers from independent techniques. Mars had abundant water. Mars lost that water through processes we can now measure directly. The techniques will only improve, sharpening the picture of what ancient Mars was like and whether it hosted life during its brief, warm youth. Jezero crater stands as perhaps the most intensively studied WAPS, the most intensively studied window into Mars' wet past. The crater formed roughly 3.5 to 4 billion years ago when an asteroid slammed into the Martian surface, excavating a basin 45 kilometers across. What makes Jezero extraordinary is not the impact itself, but what happened afterward. Two valley systems carved through the crater's western rim, creating channels through which water flowed into the basin, forming a lake that persisted for millions of years. The incoming water carried sediment that accumulated in a fan-shaped delta on the crater's western floor. This delta, now preserved as layered rock deposits rising up to 100 meters above the crater floor, records the history of water flowing into Jezero long after the ocean in the northern lowlands had disappeared. The crater became an isolated oasis in an increasingly dry world. Orbital imaging and spectroscopy identified Jezero as a prime location for searching for signs of ancient life, years before NASA's Perseverance rover landed there in February 2021. Mars Reconnaissance Orbiter's CRISM spectrometer detected clays, carbonates, and olivine in the delta deposits, indicating the lake water had neutral to slightly alkaline pH, suitable for life. High-resolution images from HiRISE revealed fine layering in the delta, with individual layers visible at scales of meters, suggesting the delta built up through hundreds or thousands of depositional events as river floods carried sediment into the lake. Some layers show inverted topography, where ancient river channels now stand higher than surrounding terrain, because the sediment filling the channels was more resistant to erosion than the materials around them. These inverted channels preserve the three-dimensional structure of ancient rivers. Perseverance's ground-level observations exceeded expectations. The rover examined rocks at the base of the delta using its suite of cameras and spectrometers. In April 2022, the mission team announced the rover had found organic molecules in multiple rock samples drilled from delta sediments. The organics appeared in association with sulfate minerals, suggesting they formed when water interacted with volcanic rocks. Organic molecules are not evidence of life by themselves. They can form through purely chemical processes, but they are necessary ingredients for life as we know it. The discovery demonstrated that Jezero's ancient lake contained the carbon chemistry that could potentially support biology. The rover collected samples containing these organics for eventual return to Earth, where laboratory analysis can search for biosignatures that distinguish biological from non-biological organic molecules. Gale Crater tells a different but complementary story. This crater, 154 kilometers across, formed about 3.8 billion years ago. At its center rises Mount Sharp, officially named Aeolis Mons, a 5-kilometer-high mountain composed entirely of layered sedimentary rocks. This is backwards from typical crater morphology. Impact craters should have central peaks made of uplifted bedrock, not tall mountains made of sediment. The leading explanation is that Gale Crater was completely filled with sediment over hundreds of millions of years, then partially eroded away, leaving Mount Sharp as a remnant of the original fill. The sediment accumulated in a long-lived lake that periodically filled and dried as Mars' climate oscillated. Curiosity rover has been climbing the lower slopes of Mount Sharp since 2014, analyzing the chemistry and mineralogy of different layers. The rover found that the lowest layers, the oldest deposits, contain abundant clay minerals, indicating neutral pH water. Higher layers, younger in age, contain sulfate minerals, suggesting more acidic conditions and evaporation. This transition from clays to sulfates appears in the geological record globally on Mars, not just in Gale Crater. It suggests Mars underwent a planet-wide shift from neutral water to acidic water to dry conditions over hundreds of millions of years during the late Noachian and Hesperian periods. The layering in Mount Sharp provides a stratigraphic record of this transition spanning perhaps 500 million years. Curiosity's measurements revealed something unexpected in 2019. The rover detected surprising amounts of manganese oxide in some rock layers. Manganese oxide minerals typically require highly oxidizing conditions to form, more oxidizing than Mars' atmosphere should have provided. On Earth, manganese oxides often form through biological processes, with microorganisms facilitating the oxidation reactions. The presence of manganese oxide in Gale Crater does not prove life existed there, but it suggests the lake chemistry was more complex and potentially more habitable than simple models predicted. The finding raised new questions about what processes generated such oxidizing conditions on early Mars. Comparative analysis with Earth's ancient lakes and oceans reveals both similarities and critical differences. Earth's oldest sedimentary rocks, preserved in Western Australia and Greenland, date to about 3.8 billion years ago and contain evidence of shallow marine environments with microbial life. These rocks show similar layering, clay minerals, and chemical signatures to Martian sediments. But Earth's ancient rocks also show clear evidence of biological activity in the form of stromatolites, layered structures built by microbial mats, and carbon isotope ratios indicating photosynthesis. No similar biosignatures have been found on Mars yet. The absence of evidence is not evidence of absence, particularly given we have examined less than 1/1,000,000th of Mars's surface at the detail needed to find microfossils. But the comparison shows that if life existed on Mars, it was either less abundant than early Earth life or preserved differently, or we have not yet looked in the right places. Recent discoveries continue to revise our understanding. In 2020, researchers analyzing crater statistics on valley networks published findings that some valleys continued forming into the Amazonian period, as recently as 2 billion years ago, far later than previously thought. This suggests episodic water activity persisted on Mars much longer than the warm, wet Noachian period. The valleys are associated with volcanic regions, supporting the hypothesis that volcanic heat occasionally melted subsurface ice long after the ocean vanished. In 2021, analysis of recurring slope lineae using high-resolution thermal imaging revealed these features form through dry landslides triggered by seasonal carbon dioxide frost sublimation, not liquid water. This finding eliminated one potential example of modern water activity but refined our understanding of current Martian processes. The Mars Express orbiter detected methane in Mars's atmosphere sporadically between 2004 and 2014, with concentrations varying from undetectable to about 45 parts per billion. The detections were controversial and difficult to reproduce. In 2019, the ExoMars Trace Gas Orbiter, which has sensitivity 100 times better than Mars Express, reported no methane detections above its detection limit of 50 parts per trillion in most measurements. However, in June 2013, Curiosity rover detected a sharp spike of methane inside Gale Crater reaching 7 parts per billion, far above background levels. The spike lasted about 60 Martian days, then disappeared. The combination of orbital non-detection and rover detection suggests methane releases are highly localized and episodic. On Earth, 95% of atmospheric methane comes from biological sources. On Mars, methane could come from geological processes like serpentinization, where water reacts with iron-rich rocks, or it could indicate subsurface microbial life. The source remains unknown. Similar phenomena on other worlds provide context for understanding Mars. Saturn's moon Titan has liquid methane lakes and seas on its surface, the only other body in the solar system besides Earth with stable surface liquids. Titan's methane cycle, with evaporation, clouds, rainfall, and rivers, parallels Earth's water cycle, but at temperatures of -180 degrees Celsius. Titan maintains its lakes despite methane photodissociation in the atmosphere because it has large subsurface reservoirs that replenish atmospheric losses. Mars may have worked similarly, with subsurface water reservoirs feeding surface water for as long as volcanic heat permitted, before the reservoirs froze permanently. Venus likely had oceans early in its history, perhaps for the first 2 billion years after formation. Models of Venus's evolution suggest the planet received similar water delivery to Earth during formation. But as the Sun gradually brightened, Venus experienced runaway greenhouse warming. The oceans evaporated completely. Water vapor rose to the upper atmosphere where ultraviolet light broke it apart, and hydrogen escaped to space. Venus lost its oceans through a completely different mechanism than Mars, but the outcome was similar. Two planets in our solar system's habitable zone both lost their surface water through different processes. Only Earth retained its ocean. This suggests maintaining habitability requires a precise combination of conditions that may be rarer than we hoped. Europa, Jupiter's moon, has a global ocean containing more water than all of Earth's oceans combined. But this ocean lies beneath a thick ice shell rather than being exposed to space. The ice insulates the ocean from Jupiter's radiation environment and prevents water loss. Europa's ocean remains liquid because tidal heating from Jupiter's gravity flexes the moon's interior, generating heat through friction. This represents yet another way to maintain liquid water on a body that receives almost no sunlight. If life exists in Europa's ocean, it demonstrates that habitability does not require surface water or even sunlight. Mars may have had subsurface liquid water for billions of years longer than surface water, creating potential habitats in aquifers and hydrothermal systems deep underground. The statistical distribution of valley networks across Mars shows clustering that constrains formation mechanisms. A comprehensive survey published in 2015 catalogued over 10,000 distinct valley network systems in Mars' ancient highlands. The valleys preferentially occur at specific latitudes and elevations. They concentrate between 30 degrees south and 30 degrees north latitude, avoiding the extreme polar regions. They appear most commonly at elevations between -2,000 and +2,000 meters relative to Mars' mean elevation. This distribution suggests valley formation required specific temperature and pressure conditions that existed only in certain regions. If rainfall occurred globally, valleys should form at all latitudes and elevations where topographic relief permits. The observed distribution supports either localized heating or preferential ice accumulation in mid-latitudes that later melted. Unexplained aspects continue to puzzle researchers. The northern plains are remarkably smooth, with vertical relief of only a few hundred meters across thousands of kilometers. This smoothness suggests sediment deposition in a standing body of water, consistent with an ocean. But the smoothness is too perfect. Ocean basins on Earth show underwater mountain ranges, volcanic seamounts, and tectonic features. Mars's northern plains are smoother than any comparably sized region on Earth. This could indicate the ocean was so brief that underwater geology had no time to develop. Or the smoothness could result from lava flows that filled the basin after the ocean disappeared, obscuring the ocean floor. The volcanic versus sedimentary origin of the northern plains remains debated. The missing carbonates problem has no satisfactory solution. Calculations suggest Mars' early atmosphere should have contained enough carbon dioxide to form carbonate deposits averaging 100 meters thick across the entire northern ocean basin. Even accounting for erosion and burial, we should detect massive carbonate beds from orbit. Instead, carbonates appear only in small, isolated deposits. Either our models of atmospheric composition are wrong, or the ocean was more acidic than expected, or some process destroyed or transformed the carbonates after they formed. Recent laboratory experiments show that ultraviolet radiation can decompose carbonates on Mars over geological time, releasing carbon dioxide back to the atmosphere. But the calculations suggest this process is too slow to destroy all the carbonates. The mystery persists. Ongoing research focuses on preparing for Mars sample return, analyzing data from active missions, and planning future exploration. The European Space Agency's ExoMars rover, carrying a drill capable of reaching 2 meters depth, is scheduled to launch in 2028 after years of delays. The rover will search for organic molecules preserved at depth, where radiation damage is minimal. NASA's Mars sample return campaign aims to bring back the samples Perseverance has collected by the early to mid-ish. These samples will receive analysis by instruments too large and sensitive to send to Mars, potentially resolving questions about ancient Martian habitability that orbital and rover measurements cannot answer definitively. China's Tianwen-3 mission, planned for around 2030, will also attempt to return samples from a different landing site, providing additional ground truth. The Japanese Space Agency has proposed a mission to Phobos, Mars' larger moon, to collect samples and return them to Earth. Phobos may contain ejecta blasted off Mars by asteroid impacts, potentially including material from depths of tens of kilometers below Mars's surface. Analyzing Phobos material could reveal Mars' deep subsurface composition and test whether subsurface aquifers existed. The mission could launch in the late, with sample return in the early id. Human exploration of Mars, likely in the OR beyond, will revolutionize the search for evidence of ancient oceans and life. Human geologists can cover far more ground than robots, make nuanced field observations, and collect samples from strategic locations that automated systems might miss. Humans can drill to depths of hundreds of meters, accessing subsurface ice and potentially liquid water. The transition from robotic to human exploration will answer questions that have persisted since Mariner 9 first revealed Mars Valley networks over 50 years ago. The case studies of Jezero and Gale craters, the comparative analysis with other worlds, and the ongoing research all point toward answers that seem tantalizingly close, yet remain just beyond our current reach. Every measurement narrows the possibilities while raising new questions. The story of Mars' lost ocean is still being written, one rock sample and one rover track at a time. The challenge of studying Mars' ancient ocean involves fundamental limitations in how we observe the past from the present. We see Mars as it is today, a frozen desert, and attempt to reconstruct what it was like 4 billion years ago. This requires interpreting clues that have been modified, eroded, buried, or destroyed over immense spans of time. Every rock we examine has been exposed to billions of years of cosmic radiation, temperature cycling between -120 degrees Celsius at night to +20 degrees Celsius on summer days, dust storms that sandblast surfaces at velocities of 30 meters per second, and chemical weathering from oxidizing compounds in the soil. The original mineralogy, organic molecules, and fine-scale textures that could definitively answer whether Mars had a warm ocean or cold, intermittent lakes have been altered. We are reading a book where most pages are missing and the remaining ones are water-damaged and faded. Observational bias affects what we find because we can only study what remains visible or accessible. The most ancient Noachian surfaces are preferentially preserved in the southern highlands because that terrain sits higher and avoided later volcanic burial. The northern lowlands, where the ocean would have existed, are covered by younger lava flows and sediments in many areas. We are looking for an ancient ocean in the one place where evidence is most likely to be hidden. It is like searching for Atlantis by studying mountain peaks rather than the sea floor. The geometry works against us. What remains visible tends to be material that was never under the ocean, or was exposed only briefly before being exhumed by later erosion. The perspective from orbit introduces systematic uncertainties. Orbital spectrometers detect minerals only in the top few millimeters of soil and rock, because sunlight cannot penetrate deeper. If organic molecules or carbonates or other key indicators of past water exist centimeters or meters beneath the surface, orbital instruments cannot see them. The Phoenix lander discovered water ice just 5 centimeters below the surface, completely invisible to orbital observation until the lander dug it up. How much evidence lies buried just out of reach across Mars' surface? We map what we can see, but the subsurface remains mostly unexplored except at a handful of landing sites. This creates detection bias where our conclusions are based on sampling the least interesting parts of Mars, the exposed surfaces, while the most interesting parts remain hidden. Crater counting, the primary method for determining ages of Martian surfaces, assumes the impact rate has been roughly constant over the past 4 billion years, except for the late heavy bombardment spike. But gravitational interactions among asteroids, planetary migration, and collisional evolution in the asteroid belt may have caused variations in impact rate that our models do not capture. If the impact rate 4 billion years ago was twice as high as we think, then surfaces we date to 4 billion years might actually be 3.5 billion years old. This shifts the timeline of ocean formation and loss by hundreds of millions of years, changing our understanding of how quickly Mars transitioned from wet to dry. The crater chronology calibration depends on ages derived from lunar samples, but the Moon orbits Earth, and Mars orbits farther from the Sun, where the impact flux may have been different. We are extrapolating across space and assuming similarity. The bubble concept refers to the possibility that our solar system's history was atypical, making Mars an unrepresentative example of planetary evolution. The late heavy bombardment, if it occurred as models suggest, was triggered by giant planet migration. Jupiter, Saturn, Uranus, and Neptune did not form in their current orbits but migrated inward or outward over tens of millions of years, scattering planetesimals throughout the solar system. This migration destabilized the asteroid belt and sent a surge of impacts into the inner solar system. If our solar system's giant planet architecture is unusual, if most planetary systems do not experience such dramatic migration, then the late heavy bombardment may have been a rare event. Mars' water delivery, atmospheric evolution, and habitability window may have depended critically on that bombardment. A Mars in a different solar system without giant planet migration might have evolved completely differently. This connects to the broader question of whether Mars represents a typical outcome for small planets in habitable zones or an outlier. If we survey 1,000 exoplanets and find that Mars-sized worlds commonly retain their atmospheres and oceans despite lacking magnetic fields, then we would know Mars is special, perhaps unlucky in some way we do not yet understand. If we find that Mars-sized planets universally lose their atmospheres, then Mars is typical, and planetary mass determines fate with little variation. We cannot answer this question yet because we cannot detect the presence or absence of oceans on exoplanets, especially not ancient oceans that disappeared billions of years ago. Mars is our only detailed case study of a small planet's evolution. We are trying to understand a phenomenon from a sample size of 1. The typicality versus specialness debate echoes arguments from the history of astronomy. Before Copernicus, European astronomers placed Earth at the center of the cosmos because that is what observations suggested. The Sun, Moon, planets, and stars all appeared to circle Earth. Copernicus showed that this geocentric view was based on observational bias. We observe from Earth, so naturally it seems central. The actual arrangement has Earth orbiting the Sun along with other planets. The Copernican principle emerged from this shift, stating that Earth is not special, not centrally located, not privileged. We occupy a typical location. Over centuries, the Copernican principle expanded. Earth is not at the center of the solar system. The Sun is not at the center of the galaxy. Our galaxy is not at the center of the universe. We inhabit no special location, no privileged vantage point. This principle has guided cosmology for centuries, but Mars challenges the Copernican principle in subtle ways. If Mars is typical, then most small planets' inhabitable zones lose their oceans and become uninhabitable after a few 100 million years. This makes habitable planets rare and long-term habitability rarer still. If Mars is unusual, if it suffered bad luck through the specific timing of its magnetic field failure or the late heavy bombardment or some other factor, then small planets might commonly remain habitable. The Copernican principle suggests Mars should be typical, not special. But our presence on Earth to observe Mars at all may introduce anthropic bias. We exist on a planet that remained habitable for billions of years, so we can build spacecraft and study neighboring worlds. We cannot exist on Mars because it became uninhabitable. Our very existence as observers biases us toward finding ourselves on an atypical planet while Mars represents the typical fate. Anthropic considerations complicate interpretation throughout planetary science. The fact that we observe the universe from a habitable planet introduces selection bias that is difficult to quantify. If 99% of planets in habitable zones lose their oceans like Mars, and 1% retain them like Earth, we would find ourselves on an Earth-like planet because we could not evolve on a Mars-like planet. This makes Earth seem typical from our perspective, even though it is actually rare. The anthropic principle states that observations of the universe are constrained by our existence as observers. We can only observe a universe capable of producing observers. Applied to Mars, this means we should be cautious about assuming Mars' fate is universal. Earth may be rare, but we cannot easily determine how rare because we are required to exist on a rare world. The philosophical implications extend to the search for life beyond Earth. If life requires billions of years of stable habitability to evolve intelligence, then intelligent life can only emerge on planets that avoid Mars' fate. Most habitable planets might support simple microbial life for a few 100 million years before losing their habitability, never developing complex ecosystems or technological civilizations. We would never encounter such worlds as inhabited because the inhabitants went extinct before developing spaceflight. The galaxy might be full of dead masses, planets that once harbored life but lost it when their oceans disappeared. We would detect these worlds as barren, not knowing they were once alive. This scenario makes the universe far lonelier than optimistic projections suggest. Future surveys will constrain how typical Mars is by characterizing thousands of exoplanets in detail. The James Webb Space Telescope, operating since 2022, can detect atmospheric composition on some exoplanets through transit spectroscopy. When a planet passes in front of its star as seen from Earth, starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths, creating an absorption spectrum that reveals what gases are present. Webb has already detected water vapor, carbon dioxide, and methane in exoplanet atmospheres. Future observations will search for combinations of gases that might indicate habitability or life, such as oxygen and methane together, which on Earth are maintained by biology. But detecting whether an exoplanet has an ocean, particularly an ancient ocean that disappeared, requires observations beyond current technology. We would need to resolve the planet's disk, map its surface, detect minerals from reflected light, and track atmospheric evolution over decades or centuries. This requires telescopes far larger than Webb, perhaps space-based interferometers with effective diameters of hundreds of meters. Such instruments could be built in the OR beyond with sufficient investment. Until then, Mars remains our highest resolution laboratory for studying planetary ocean loss. Mars as a natural laboratory provides advantages no other accessible environment offers. We can send spacecraft to Mars, land rovers, drill into rocks, return samples, and eventually send humans. We cannot do this for exoplanets. Mars preserves a 4 billion-year geological record, spanning the transition from habitable to uninhabitable. We can read this record layer by layer, sample by sample. The planet is close enough that round-trip communication takes only minutes, allowing detailed remote operation of rovers and eventually real-time exploration by humans. Mars represents the best possible case study of planetary ocean loss we are likely to have for decades. The natural laboratory concept also applies to testing predictions about atmospheric escape. MAVEN's measurements of current escape rates can be extrapolated backward with models of solar evolution to calculate cumulative loss over billions of years. These calculations predict Mars should have lost a specific amount of atmosphere. The deuterium to hydrogen ratio provides an independent measurement of actual loss. The two estimates agree within uncertainties, validating both the escape models and the deuterium measurements. This kind of closed-loop validation is impossible for exoplanets where we have only indirect observations. Mars lets us test our understanding of planetary processes in ways that build confidence when we apply similar reasoning to worlds we can barely detect. The advantages extend to understanding climate physics. Earth's climate is complicated by oceans, life, plate tectonics, and human activity. Isolating individual climate mechanisms is difficult when everything interacts. Mars has simpler climate physics because the planet lacks oceans, life, and plate tectonics. The atmosphere is thin, reducing the number of interacting variables. This simplicity makes Mars an ideal testbed for climate models. If we cannot accurately model Mars' simpler climate, how can we trust models of Earth's or exoplanet climates? Success modeling Mars builds confidence. Failure reveals gaps in understanding that need addressing. But the natural laboratory is incomplete. We have only scratched the surface literally and figuratively. The deepest drilling on Mars reached about 7 centimeters with Curiosity's drill and 2 meters with the planned ExoMars rover drill. Meaningful groundwater or subsurface ice deposits might exist at depths of hundreds of meters or kilometers. On Earth, subsurface microbes have been found living in rocks 5 kilometers underground. If Martian life exists, it might be deep below the surface, inaccessible to current missions. We are sampling the outer skin of the laboratory, the least interesting part where radiation and weathering have destroyed or modified the most informative materials. The perspective limitations also involve temporal resolution. We can determine that the magnetic field shut off around 4 billion years ago. But was it a gradual decline over 200 million years, or an abrupt collapse over 10 million years? The crater counting uncertainties are too large to distinguish these scenarios. Yet, the distinction matters. Gradual magnetic field decline would give the atmosphere more time to adapt, possibly allowing multiple stable states as the planet transitioned. Abrupt collapse would create rapid environmental change with little adaptation time. The pace of change determines whether life, if it existed, had time to retreat to refugia or went extinct suddenly. Detection limits constrain what we can claim about absent evidence. We have not found definitive biosignatures on Mars, but we have examined less than 1/1,000,000th of the planet's surface at the microfossil scale. We have not found abundant carbonates, but orbital spectrometers can only detect deposits covering at least a few square kilometers, with certain thickness and exposure characteristics. Smaller deposits or buried deposits remain undetectable. Absence of detection is not detection of absence when instrumental sensitivity and coverage are limited. Every negative result must be qualified by the instrumental limitations that produced it. The biases, limitations, and perspective effects mean our current understanding of Mars' ocean remains provisional. We have strong evidence the ocean existed but cannot definitively prove its temperature, duration, depth, or chemistry. We know water was lost, but cannot precisely determine how much or through which mechanisms. We can measure deuterium enrichment, but must make assumptions about starting conditions to convert that enrichment into absolute loss. Every measurement requires assumptions. Every assumption introduces uncertainty, and uncertainties compound when we build narratives from multiple measurements. Yet the story hangs together remarkably well given these limitations. The valley networks, clays, deuterium enrichment, magnetic field history, crater chronology, atmospheric escape measurements, and meteorite evidence all point toward the same general picture. Mars had an ocean 4 billion years ago. The ocean existed for hundreds of millions of years. The magnetic field failed. Atmospheric escape accelerated. The ocean disappeared. This narrative survives despite observational biases because it is constrained by multiple independent lines of evidence. No single measurement proves the case. The convergence of evidence from different techniques builds a compelling argument. Understanding the limitations helps us ask better questions. Rather than asking whether Mars had an ocean, which the evidence strongly supports, we should ask specific questions. Current measurements cannot answer. What was the ocean's salinity? Did it freeze from the top down or bottom up? How many freeze-thaw cycles occurred? Were there tides? Did the ocean circulate or stratify? These detailed questions require observations we cannot yet make, but could with future missions. Recognizing what we do not know focuses attention on what needs to be measured next. The natural laboratory is still open, still running experiments across its frozen surface and hidden depths, still holding secrets about how planets live and die. We are learning to read the laboratory notebooks written in rock and ice and atmosphere, deciphering the experimental results recorded over billions of years. The reading is difficult, the handwriting often illegible, but the story it tells about planetary habitability and its fragility grows clearer. The future of Mars extends across timescales that dwarf the planet's brief, habitable period. 4 billion years from now, 4 billion years from now, when the Sun has exhausted the hydrogen fuel in its core and begins fusing helium, it will expand into a red giant. The Sun's outer layers will swell outward, engulfing Mercury and Venus. Mars will survive, but the planet will receive hundreds of times more solar energy than today. Surface temperatures will soar above 1,000 degrees Celsius. Any remaining ice will vaporize instantly. The atmosphere, such as it is, will boil away completely. The surface will melt, creating global lava oceans. Mars will spend its final few 100 million years as a molten hell world before the Sun finally sheds its outer layers and collapses into a white dwarf. At that point, roughly 5 billion years from now, Mars will freeze permanently at temperatures approaching absolute zero, heated only by the dying white dwarf's fading infrared glow. The planet that once had oceans will end as an airless ball of frozen rock orbiting a stellar corpse. But before that distant death, Mars faces a different fate on shorter timescales. The planet is slowly spiraling outward from the Sun. Tidal interactions between Mars and the Sun, though incredibly weak, transfer angular momentum from the Sun's rotation to Mars' orbit. This pushes Mars fractionally farther from the Sun each year. The effect is minuscule, only about 2 centimeters per year, but over billions of years it accumulates. 1 billion years from now, Mars will orbit roughly 3% farther from the Sun than today. This will reduce solar heating slightly, cooling the planet by a few degrees. Not that it matters for a world already frozen to minus 60 degrees Celsius on average. The orbital evolution proceeds regardless, following the inexorable mathematics of gravitational dynamics. Mars' 2 small moons face their own timelines. Phobos, the inner and larger moon, orbits so close to Mars that tidal forces are pulling it inward rather than pushing outward. Phobos circles Mars at an altitude of only 6,000 kilometers above the surface, completing an orbit every 7.7 hours. The Moon is spiraling inward at about 2 centimeters per year. In roughly 50 million years, Phobos will cross the Roche limit, the distance at which Mars' tidal forces overcome the Moon's self-gravity. Phobos will disintegrate, torn apart by gravitational stress. The debris will spread into a ring around Mars, similar to Saturn's rings, but much thinner and shorter-lived. Over millions of years, the ring particles will gradually spiral inward and rain down onto Mars's surface as a prolonged meteor shower. Deimos, the smaller outer moon, orbits beyond the Roche limit and will survive until the Sun's red giant phase destroys everything. The implications for life on Mars, if it ever existed, are extinction measured in absolute terms. Any surface life died when the ocean froze, roughly 3.5 billion years ago. Any subsurface life clinging to deep aquifers might persist until those aquifers freeze completely, which could take hundreds of millions of years longer. But eventually, Mars' interior will cool to the point where no liquid water can exist anywhere. Radiogenic heating from uranium, thorium, and potassium decay decreases exponentially with time, as these radioactive elements transform into stable isotopes. The half-life of uranium-238 is 4.5 billion years, meaning half of Mars' original uranium has already decayed. In another 4.5 billion years, only a quarter will remain. The heat production drops accordingly. Models of Mars' thermal evolution suggest the planet's interior has already cooled to the point where widespread liquid water cannot exist, though small pockets in volcanic regions or impact-heated zones might persist. If Martian life exists today, it occupies a narrow window between the freezing of surface oceans 3.5 billion years ago and the complete freezing of subsurface habitats perhaps 1 to 2 billion years in the future. That gives life, at most, 5 billion years on Mars, with habitable periods at the beginning and possibly at the end bookending a long frozen middle. Compare this to Earth, where life has existed continuously for at least 3.8 billion years and could persist for another 1 to 2 billion years until the brightening sun makes Earth uninhabitable. Mars gets 5 billion years of marginal habitability scattered across epochs. Earth gets 5 to 6 billion years of continuous habitability. The difference stems from planetary mass and the geological activity it enables. Civilizations on Mars, whether human colonies or hypothetical extinct Martian intelligence, face constraints imposed by the planet's meager resources. A human settlement would require continuous life support, with no possibility of the planet being terraformed to Earth-like conditions permanently. Early terraforming proposals from the THRU suggested releasing Mars' frozen carbon dioxide from polar caps and subsurface deposits to thicken the atmosphere, warming the planet through greenhouse effect until liquid water became stable. Calculations showed this could potentially work if Mars contains enough carbon dioxide. The problem is retention. Without a magnetic field, any atmosphere thick enough for habitability would be stripped away by the solar wind over tens of millions of years, fast on geological timescales but slow compared to human lifespans. A terraformed Mars would be a temporary garden lasting thousands of human generations, before gradually declining back to frozen desert. Maintaining it would require continuous atmospheric replenishment, importing volatiles from asteroids or other sources indefinitely. Other observers in the galaxy face the same arithmetic that doomed Mars. Any technological civilization on a Mars-sized planet in a habitable zone must confront atmospheric loss and the inevitable freezing of their world. If intelligence requires billions of years to evolve, as it apparently did on Earth, then Mars-sized planets cannot support the evolution of technological civilizations because they lose habitability too quickly. Only Earth-sized or larger planets with sufficient mass to maintain geological activity for billions of years can potentially host long-lived biospheres that develop intelligence. This creates an observational selection effect. All technological civilizations we might ever encounter will come from large planets because small planets cannot support the long-term habitability required for intelligence to emerge. We will never meet Martians because Mars-type worlds freeze before life gets interesting. But this reasoning assumes intelligence requires billions of years to evolve. Perhaps under different conditions in different biochemistries, intelligence could emerge faster. Perhaps Martian oceans hosted something we would recognize as intelligent during the Noachian period. Civilizations that rose and fell in the few 100 million years when the planet was habitable, leaving no trace detectable 4 billion years later. The complete absence of evidence for such a scenario makes it purely speculative. But the universe is vast and ancient. If Mars-type worlds are common, and if even a tiny fraction developed life, and if even a tiny fraction of those developed intelligence during their brief, habitable windows, then the galaxy might have hosted countless extinct civilizations on frozen worlds, their ruins buried beneath ice and dust, their existence erased by time. We would never know. The past is opaque across billions of years. Meta-questions about our knowledge of Mars reveal how much we have learned and how much remains unknown. We can determine that Mars had water 4 billion years ago through multiple independent measurement techniques that converge on the same answer. This represents genuine knowledge, not speculation, but we cannot determine whether Mars had life. The absence of detected biosignatures might mean life never emerged, or that we have not looked in the right places with sensitive enough instruments, or that Martian life was so different from Earth life that we would not recognize its signatures even if we saw them. Knowledge has boundaries, and we are mapping those boundaries with each mission. The philosophical synthesis emerges from recognizing Mars as a mirror, showing Earth's potential fate. What happened to Mars could happen to Earth under different circumstances. If a giant impact stripped away our atmosphere, or if our magnetic field failed, or if the sun's evolution accelerated, Earth could become a frozen desert like Mars. The difference between the two planets is not fundamental in the sense of involving different physics. Both planets follow the same natural laws. The difference is quantitative, matters of degree rather than kind. Mars is smaller, orbits farther out, cooled faster, lost its magnetic field earlier. These quantitative differences accumulated into the qualitative difference between a living world and a dead one. This connects to the deepest questions about existence and meaning in a universe governed by physical law. Mars teaches us that habitability is fragile, temporary, contingent on factors outside any inhabitant's control. A planet's fate is determined at formation by its mass and orbital location. No amount of adaptation can overcome these constraints. Mars could never have avoided losing its ocean because Mars could never have been larger or closer to the Sun without being a different planet entirely. The tragedy is written into the initial conditions. Habitability is not a stable attractor state that planets naturally settle into. It is a precarious balance that most planets never achieve, and those that do achieve cannot maintain indefinitely. Yet within these constraints, life persists where it can for as long as it can. Earth's biosphere has survived 5 major mass extinctions: asteroid impacts, volcanic eruptions, ice ages, and every catastrophe the planet threw at it over nearly 4 billion years. Life on Earth persists not because of any special protection, but because Earth remained habitable, and life is remarkably resilient within habitable environments. If Mars had life, it too probably persisted for as long as conditions permitted, before finally succumbing to the freezing. There is a defiance in that persistence, a kind of cosmic stubbornness where organization resists entropy, complexity fights simplification, and life grabs whatever foothold it can find. The return to the opening theme brings us full circle. Mars had an ocean 4 billion years ago. Waves lapped against shorelines under a thick atmosphere that kept the surface warm enough for liquid water. Rivers flowed, deltas accumulated sediment. Clay minerals formed in lake beds. The chemistry was right for life. Then the magnetic field died. The solar wind stripped the atmosphere. The ocean evaporated and froze. The planet became the rust-colored desert we see today. This happened not because of any single catastrophic event, but through the steady, patient working of thermodynamics over hundreds of millions of years. Mars was born too small to hold its water, and that single fact determined everything that followed. We look at Mars today and see a dead world. We look at Mars 4 billion years ago through the evidence in rocks and atmosphere and see a world that might have been alive. The gap between those two visions contains the story of planetary evolution, the fragility of habitability, and the contingent nature of existence in a universe that does not care whether planets remain habitable or life survives. Mars lost its ocean not because the universe is cruel, but because the universe is indifferent. Physical law operates without regard for consequences. Planets form, evolve, and die according to mathematics that has no term for hope or tragedy. But we are here to witness it, to read the story written in deuterium ratios and magnetic field fossils, to send our robots to Mars and, eventually ourselves, to understand what happened and why. That understanding does not change Mars' fate or bring back the lost ocean, but it changes us. We learn that habitability is rare and precious, that Earth's long-term stability is remarkable rather than typical, that we occupy a planet that avoided Mars's fate through accidents of formation that we did not choose and cannot control. The humility this knowledge brings is worth the decades of exploration and billions of dollars spent to acquire it. Mars is both a warning and an invitation. A warning that habitability does not last forever, that planets die, that the environments supporting life are temporary on cosmic scales. An invitation to explore while we can, to learn what we can, to understand the universe that created us and will outlast us. The frozen desert that was once an ocean still has secrets to reveal about life, about planets, about the strange and narrow conditions that permit complexity to emerge from physics. We are still reading those secrets, still listening to what Mars has to tell us about where we came from and where we are going. The ocean is gone, but the questions it raises remain. They will remain long after our current missions end, long after humans walk on Mars and perhaps build cities there, long after we expand to other worlds or go extinct ourselves. The universe will keep running its experiments, forming planets, some habitable and some not, some briefly alive and most eternally dead. Mars is one data point in that vast experiment. But it is our data point, close enough to study in detail, different enough from Earth to teach us what we could not learn at home. If this journey through Mars' lost ocean spoke to you, consider subscribing for more cosmic mysteries designed to help you drift off into contemplation and rest. There are more stories waiting, more worlds to explore, more questions about existence and the universe we inhabit. Leave a like if you found peace in understanding how planets live and die, how oceans form and disappear, how time and physics reshape worlds across billions of years. And good night, wherever you are in this vast, strange universe where some worlds hold their water and some let it slip away into the darkness between the stars.